Hello, everybody. We finally made it to the last chapter for Organic Chemistry 2, Chapter 21, Alpha Carbon Chemistry, Enols and Enolates. As you guys can see right on this slide, we have covered already at some point about enols chemistry in Organic Chemistry 1, right? There was equilibrium, what is called the tautomerization keto-enol. So it's not something new. It's not a new term that we're going to study today. But now we will cover the chemistry behind it. So all the alpha carbon chemistry, meaning that alpha carbon position respect to a C-double-O. So even though we're going to be focusing on functional groups that we already studied, for example, aldehydes, ketone, esters, carboxylic acids, amides, right, which were covered on chapter 21 and chapter 20 and 19, but now we will see what happens with the alpha position, not the actual functional group, but the group that is the carbon that is next to that C-double-O group. Right. So here just a little bit on the the location, just to give you a scheme of where things are located. So this one will be our C-double-O group, right? So it's a ketone in this case, and the adjacent, the immediate neighbor of that C-double-O group will be the alpha position. Alpha, beta, gamma, delta will be the next one, but we will always work with the alpha position. Okay, so in this particular case, we have a ketone, right? But that doesn't mean that it cannot cover something else. So for example, if we are talking about, alpha position of an aldehyde, right? So this one is an aldehyde. So this one, we'll call it the alpha position, alpha. Okay, so in that case, you will only have one alpha site. So you guys have an ester, for example, methyl ester. So this one will be your alpha site, right? So every type of functional group will have its own, right? So alpha position is the one that is immediate, is adjacent to the C-double-O group. Okay, so it's not only restricted to aldehydes and ketones. It can be an ester. It can be many things. I mean, really, as we will see later on, but we're going to be focusing on the C-double-O group. The C-double-O group is going to be our target for this particular chapter, right? So let's continue with the slides. Okay, so just keep in mind, right, that those are the groups that we're going to be studying. We are focusing the alpha position. Well, there's also beta, and of course the reactivity of the alpha is stronger. The beta is also somewhat reactive, but definitely the alpha position is way more reactive, right? So this one is the enolate formation, right? So it's always the alpha position that is more acidic, is more reactive, and therefore that's the one that's going to form the enol and enolate, as we call it. Okay? So how do we form that? So let's use let's say the aldehyde, right? Because the example that you guys have in this slide was about a ketone, but this ketoenol or enolate formation really can be done in any C-double-O group. Okay? So we will have two types of equilibrium in acidic conditions and in basic conditions. So let's say that we do it in acidic conditions. Okay? In acidic conditions, we form the first step is the protonation. Okay, and that enolation, that protonation will induce the acidity or increase acidity of the alpha hydrogen. This one is an alpha hydrogen. Remember, this one is the carbon side, right? So the carbon side, that's the alpha position. So the alpha carbon side, so it will have an increased acidity for the hydrogens. So the water will take on that hydrogen. This bond will come now from the double bond, and the oxygen regains neutrality. And we form what we call an enol. Here is an enol. That's in acidic conditions. Okay, so this one is a tautomerization, right? The keto enol. So it's the formation of isomers, right? That only differentiate in the position of one hydrogen. The hydrogen that was here now moves to the oxygen. So that's why they're called tautomers. So tautomerization right? This is the formation of isomers just by the switch or the change of the location of a hydrogen by an acid-base property. Now, this enol can also be done in enol formation, or this equilibrium can also be done in basic conditions. We will take OH minus, right? And in this case, OH minus is basic enough to remove that hydrogen. This one will form here, carbon ion, okay? And then there is a resonance stabilization here, right? The resonance, as we can more or less guess. And this is what we call the enolate. Okay, that's the enolate. That's the actual form of an enolate, what we call enolate. So this is the enolate, which is deprotonated, it's an anion. But for the mechanisms, as we will see later, we will use mostly this particular resonance structure. Okay, so remember that these two resonance structures are in resonance. That means that they are dynamically, coexisting. But even though this is the enolate, but we will use the anion version, the carbon ion, or let's call it like that, the carbon ion for the mechanisms for the reaction we'll study today. Right? So I'm not teaching you this mechanism. Remember, this mechanism was already covered on chapter 9, alkynes. So these are all actually mechanisms that we already should know. Okay, so this one, there is an assumption that we already know really, really well. Okay, so catalytic in acidic conditions, we can get the enol, and the strong base, you can get the enolate. Okay, so I use OH minus as a base, just as a, because it's a very usual, right, base to use. But as we will see later, sometimes OH hydroxide, for example, sodium hydroxide, might not be strong enough, basic enough to produce that enolate. Okay, so let's see what are the most appropriate bases. So this is the mechanism that I show you. This one is in basic conditions. As you guys see, it's an equilibrium, right? The equilibrium is in both ways. It's not the best way how to shift the equilibrium to the product side because it's equally distributed. Here is the resonance stabilization. That's the anion form, and that's the enolate form. Of course, if this enolate form is placed in water or in acid, it will get protonated to form the neutral enol. But if it stays in basic conditions, of course, it will be still deprotonated as an enolate. Those are the acidic hydrogens, right? So you guys have two hydrogens, and then what are the best bases to use? As you can see in this slide, right? So pK 16, pK 15. Of course, remember that the equilibrium always favors the side that has the weakest acid. So in this case, this particular compound is the weakest acid, right? It's weaker than this one because remember, the higher the pK, the weaker is the acid. So the equilibrium will shift to the reactant side. So what is that telling you? That is telling me that the ethoxide might not be the most appropriate base for me to do this removal. Okay, so I need to use a stronger base to remove that hydrogen. Okay, and then what would be a good, the relative acidity? For example, acetone has a 19.2 acidity, pKa. Here, acetophenone is more acidic, right? And of course, acetaldehyde is even more acidic. Okay, so well, here we can more or less guess, right, that why acetophenone is more acidic, because it has the resonance stabilization, right, that stabilizes the C plus, the resonance here. Acetaldehyde is even more acidic in this case because the polarizability of the C double O is stronger, right? That means that it increases the acidity of the alpha position. Why is it stronger? Because there is no alkyl group as a neighbor. It's acetaldehyde. It's a plain aldehyde group. Right? So which one is an appropriate way, or which one is an appropriate base then to do the removal of the alpha hydrogen? There is a new compound that we will use, which is diisopropylamine. Isopropylamine can be deprotonated in a very strong base, for example, alkyl lithium. We already studied, right, the alkyl lithium in the previous chapter for the Wittig reaction. This is butyl lithium, and then this particular compound is called LDA. Okay, it's an abbreviation, lithium diisopropyl amide. Okay, that's a very bulky base, and then it's also strong enough to do the deprotonation in the alpha site. Okay, so from now on, you guys can use the LDA. Just use LDA. You don't need to remember or to write the structure, but remember it's a nitrogen negatively charged. Therefore, it will form a weaker base. A weaker acid. In this case, pKa 16.6, 16.7, pKa 36. Of course, the equilibrium will be fully shifted to the product side, meaning that you guys will produce mostly the carbon ion, right? Or the enolate. So LDA is a base that is good for alpha hydrogen removal. Okay, now this is the other case that I was telling you about, right? So it's not only aldehydes, ketones, esters, the ones that have alpha hydrogens. This one, for example, is a diketone. Diketones, 1,3-diketone. That would be the actual name for this compound, 1,3-diketone. The 1,3-diketones are actually more acidic, right? Because of the presence of the two neighboring COOs, right? So this alpha hydrogen, for example, this alpha hydrogen has the effect from this oxygen, but also has the effect from the other oxygen. So remember that the polarizability or the electronegativity is an additive effect, meaning that both of them will exert their acidity on their induction, let's call it like that, right? For acidic properties. So they're additive, therefore the acidity is going to be way more increased, right? So result of that is that the pKa of the first hydrogen is 9. Okay, so remember in the ketone, right? If we go back, the regular ketone has a pKa of 19, right? This one has a pKa of 9, so it's almost double, right? So it's really a diketone, right? 1,3-diketones are way more increased. Now, can I also have like a aldehyde ketone? Yes, you can have a 1,3-aldehyde ketone. Can I have a 1,3-diester? Yeah, you can have also 1,3-diester. A 1,3-diester will be, right, this compound, but here with an ester, right? OR, and here is OR. That will be a diester, right? 1,3-diester. And is that also going to be a more acidic? Yes. As acidic as the diketone? No, of course, they will each have a different type of acidity. So, of course, a dialdehyde will be more acidic, a ketoaldehyde will be next, a ketone will be next, and then a ester will be even less acidic, right? But is the acidity increased? Yeah, definitely it's going to be increased depending on the combination that you're doing, okay? So here is the ketone. This explains how you stabilize the conjugate base, right? So here the conjugate base can be stabilized with this COO. You can do the same stabilization with the other COO. It's resonance structure, and you can see how the negative charge bounces, right? Back and forth from both oxygens. So that extra resonance stabilization increases the stability of the conjugate base, therefore the acidity is increased. Okay, so the 1,3-diketone, so let's call it in general 1,3-dicarbonyls, right? That would be the best term to use. Okay, so it would be 1,3-dicarbonyl. I would say that's a better term because the dicarbonyl can be a dialdehyde, right? That's a 1,3-dialdehyde. It can be a aldehyde ester. Yeah, you can also have that. This hydrogen, of course, these hydrogens are more acidic, right? Aldehyde, let's say what? Amide. That's also 1,3-dicarbonyl. Yeah, of course. The keto ester. Yeah, you can also have that. Ketoester, they're all a combination of dicarbonyl, right? The carbonyl can come from many sources. Can I also, that carbonyl can be from a carboxylic acid? No. In that case, the carboxylic acid cannot be included in this case. Why? Because if you guys use a carbonyl, right? Let's say aldehyde, and then here have a carbonyl, right? Which hydrogen is the most acidic? Is it going to be the alpha hydrogen? Of course not. Why? Which one is the most acidic? The carboxylic acid is more acidic, way more, because this is a CH bond. This one is an OH bond. OH bonds are always more acidic than CH bonds. Okay, so don't include carboxylic acid because carboxylic acids, of course, are going to be more acidic than any alpha hydrogen. No matter what combination you use for the alpha hydrogen, the carboxylic acid will always be more acidic than the alpha carbon. Okay, so just keep that in mind. Yep. So now let's keep going. So here we have an ethoxide. Now, the ethoxide is basic enough to remove a 1,3-dicarbonyl, right? You see now the pK was 9. Now this pK is 15.9. Of course, it's going to be now acidic enough. Okay, so basic enough to do the removal of alpha hydrogen. That was not the case in this equilibrium. You can see here ethoxide was not successful. Why? Because it was just a simple aldehyde. But if you guys have a 1,3-dicarbonyl, then the acidity is increased. Now this base is good enough to do the deprotonation. Okay. Okay. So now let's start with the first reaction. The first reaction that we will study is the halogenation. Alpha-halogenation of, in this case, is bromination, and this will lead us to a reaction that we studied in the past. Okay, so I think that if we go back to alcohols, right? Alcohols, there was a test that we did, and also for aldehydes and ketones, for methyl alcohols and methyl ketones. Okay, so that test was called the iodoform test, right? So if we recall from the previous, right, from the lab, so there was a test which was called iodoform. And the same way there is a iodoform test, there is also bromoform and chloroform test. Fluoroform, no. I mean, I haven't seen because, I mean, you know, but by now you guys should know that the fluorine, right? Fluorine is a very picky element. So mostly the reaction has either chlorine, bromine, or iodine. Iodoform is used because iodine is a really heavy element. So anything that is produced with iodine, it will be a solid. So it's very easy to recognize, it's very easy to notice, it's very easy to identify, right? So that's why this reaction is called iodoform. Now, in this case, right now in this reaction, we will have to do the mechanism is halogenation. Okay, we will call it alpha halogenation. Why alpha halogenation? Because it occurs at the alpha position of our compound. Right? So that reaction is going to be done in acidic conditions. It can also be done in basic, right? But let's do it in, well, let's do it in both. Right? So let's do the first in the acidic conditions. So I have this compound. Okay, so that's also a very important thing. I'm gonna take advantage of that, of this situation. If I have two alpha hydrogens, which of the two alpha hydrogens should be formed, right? Because you say like, Professor, which one I have here, two alpha hydrogens. Should I remove this alpha hydrogen or should I remove this alpha hydrogen? Remember that upon removal of the hydrogen, you guys are gonna be forming an enol. An enol is a double bond. Which double bond is more stable, if you guys recall? The one that is more substituted or less substituted? By definition, the most stable alkene is the one that has more substituents, right? In this case, this alkene only has one alkyl chain. This other alkene has 3 alkyl chains. Therefore, which one is the most stable? Which is the most stable enol that you're forming? Of course, the most stable. Okay, that is not the case in the iodoform. We will see that reaction. Let me see here. Okay, yeah, you see here how it creates the most the most substituted major product. It gives you the most substituted, meaning that the bromine will be added to the most substituted carbon. Okay? So that's very important to notice. The enol that is with the most, most substituted is better, is more stable than the least substituted alkene or less substituted enol that you guys are going to be forming. Okay, so methyl ketone. Course. It's a minor product, okay? It's a minor, yeah, that's something also very important for you guys to notice. There's a minor product that you're getting. You still get a minor product from the less substituted side, right? But the major product should be the most substituted. Hey, so let's go back to the mechanism. Okay, so in this case, we will have, right, in acidic conditions, it says H3O plus, right? Right? Remember that the oxygen will get protonated. Okay. After this, we need to remove that, form the enol. Here, the water will remove this hydrogen and will form the, well, actually, it will form the enol. Okay. That's the enol, but as we said before, right? Another way, or the best way how to write the mechanism is by using the carbon ion. But we need to displace here. Yeah, no, in this case, it has to be this way. Okay, so let's leave it like that for this one. For this particular mechanism, we actually have to leave it like this. Okay, and then we have bromine, and bromine. Remember that bromine and bromine, bromine, elemental bromine, it gets polarized, delta plus, delta minus, right? There's an induced dipole. So the alkene will attack the delta plus bromine. This bromine leaves. Okay. Plus here, one bromine gets added to the alpha position. And of course, who helps here to stabilize this charge? The oxygen contributes to stabilization by resonance. The bromine was added, right? And now the other bromide, right? The bromide that you guys formed will take off. This one is resonance structure, and the bromide will take that hydrogen. And you guys will have your brominated ketone. Okay? Makes sense? I mean, what we, right? We just, the mechanism that we just wrote. And then I'm doing the mechanism with you guys because that's also what I want to see in the mechanisms that we actually are being asked during the quizzes and the exams. Okay, so the way how I do the arrows, for example, I'm not doing the arrow from the oxygen, I'm doing the arrow from the electrons. I'm attacking the hydrogen, I'm not attacking the bond, I'm not attacking the air, I'm not attacking the charge, right? So those are details that we always have to remember for the mechanism. So we're in the last chapter of organic chemistry 2. You guys already study 21 chapters. So after 21 chapters, it's expected that we should be able to write like a good organic reaction mechanism. Okay, so we're expecting that. So we need to know the mechanism for the alpha halogenation. Okay, now what happened with the iodoform test? In the iodoform, we have something very similar, but it only applies to the methyl ketones. Okay, it's a methyl ketone test. So in this case, let's use the same ketone, but now we have the OH. The OH will do the deprotonation. Here in this case, you say like, Professor, you should do the, you should do produce or remove the alpha hydrogen this side because it gives you the most stable enolate, right? Or the most stable carbon ion, the most stable, right? Double bond. Yeah, but guys, remember that this one is not gonna take you to the iodoform test. The iodoform test really depends on the methyl ketone. So it's the methyl ketone that has to be reacting for this particular reaction. Okay, so I know that this one will be the major, this one will be the minor, but the main goal is to, right, is the mechanism tells you this. So definitely here you are seeing that the methyl is the one that reacts. Okay, so in any question that they ask you really for the mechanism, you always have to look at the product, and then the product will tell you what type of reaction is being done. Okay, so I know that the rule says that, but remember this one is the major product. This one is a minor product. According to this mechanism, it's actually asking me the reaction of the minor product. So I cannot just continue to do the major product if I see that my product doesn't match. So it's really useless to do it this way, because this way will not take me to this product. I can see that I'm losing a carbon. If I'm losing a carbon, of course, the only way to lose a carbon is this one. I can lose one carbon from this side, because this side is 1, 2, 3. It's 3 carbons. So these 3 carbons don't match the 3. There is no 3 carbons here. So 1, 2, 3, right? So the 3 carbons stay. So I have to tailor my reaction based on the products what I see in a mechanism question. Okay, so let's do it. Let's do the mechanism. This is an alpha hydrogen. I will put an alpha there so you guys can recognize it. OH minus, right? In this case, the oxygen. Here I don't use the carbon ion. In the previous case, I didn't use the carbon ion because remember, it was, guys, it was in acidic conditions. In acidic conditions, there is no way I can have a C minus. C minuses are so basic that they cannot exist. So that's why I had to use the Enol version, right? So you recall from this particular, right? In this case, I didn't produce the C minus because in acidic conditions, it's not stable. C minus, it gets protonated immediately. Okay, so here I have the iodine, iodine. Same story happens, right? The iodine gets polarized, delta plus, delta minus. So the carbon ion attacks one of them, the other iodine leaves. I have one iodine. Okay, so then comes another OH minus is in excess. OH has to be in excess. So now, which hydrogen is going to be more acidic? Now, this one is going to be even faster. It's going to be even more acidic. Why? Because now this hydrogen does not have only the stabilization by resonance, right, from the COO, but also has induction from the iodine. Remember, iodine is electronegative, so it will, by induction, it will increase the acidity of this hydrogen. So the OH minus will definitely go even faster with this particular hydrogen or proton transfer. Okay, so I'm adding now here iodine minus carbon ion again. This hydrogen, this iodine definitely propels that second deprotonation. Then I have another iodine, right? The carbon ion attacks the iodine, the other iodine leaves. There is one hydrogen left, right? Because remember, it was a methyl, meaning that it has 3 hydrogens. Now we will use another OH. That one more OH will deprotonate the last one. Of course, this hydrogen is even more acidic. Why? Because now it has 2 iodines that are electronegative. So therefore, by induction, it will increase even more its acidity. Okay, deprotonated. Now this carbon is a carbon ion again, and now it will come the last iodine to be attacked. Three iodines. Okay, 3 iodines got added to that methyl group. Remember, this one is the minor product again. The halogenation should really occur at this alpha position, but because of this is the major and the minor, this is the minor, is gonna give me this product. Okay, so what's next? Well, after that, the OH minus. Okay. Now, this one is very unusual because this one it behaves as a leaving group. Why is it a good leaving group? Because it has 3 electron withdrawing groups. Okay, remember that the better the electron withdrawing group, the better leaving group it is. Well, that happens with the 3 iodides. The 3 iodides exert so much of the electronegativity that they pull the electron density, makes it more, right, more polarized, this carbon. So it makes them better leaving group, but due to the presence of these 3 iodides. So the COO will behave as an acid halide, right? You recall from the previous chapter. So this guy will attack the COO. OH. Here is the Ci3. I will put it in one small, and this is O minus. Okay, then this O minus and then kicks out the CI3. So you guys will have a carboxylic acid plus I3C, but the C has a minus. Okay, so here's where it comes the proton transfer. Oh no, that's okay, because in the second step, right, in the second part, you guys have water. So, well, water is everywhere anyway, but the C minus will attack and goes. Okay, so you will have your carboxylic acid and HCI3. Okay, so that was the goal of the iodoform test. We need to know this mechanism, okay, the iodoform. So finally, we are studying the iodoform test, and we need to remember for the exam and or quizzes. Okay, good. Okay, so we have so far the alpha halogenation. Here we have now the iodoform test. Now the same thing can be done with bromine and chlorine. So you wouldn't get the iodoform, you will get the bromoform and the chloroform, right? But for the identification of aldehydes and ketones or methyl aldehydes or methyl ketones is commonly used the iodoform test because this guy is a solid. You can tell that it's a solid because it has 3 iodides. It makes it so heavy that absolutely it's going to be really, really heavy, right? And precipitates out from the solution. Okay, so that's just to go over. You get always the more saturated, the more stable. Here, in this case, they are very tricky. They have to admit it because here, this particular side has no alpha hydrogens. If it has no alpha hydrogens, of course, you guys, the only reaction that can occur is on this side. But it's only, I mean, can I get alpha bromoform or a iodoform from any methyl ketone? Yes, you can get a bromoform from any methyl ketone. I have seen it. Okay, so in this case, they make it very simple. I mean, here the author is really smart because here you guys have no, right? No options. Here, this one has no alpha hydrogen. This one has 3 alpha hydrogens. So of course the reaction will proceed this side. But what if I have both sides, right, available? Yeah, you should get the major on this side, but the minor on this side. But the minor is going to give me a better result. Actually, yes. In this case, it is because your product is a solid. Anytime that you guys produce a solid, the solid or precipitate, right, it will drive the reaction to that particular equilibrium, actually making it a major product. Okay, so it's kind of strange. Yeah, I cannot explain it because you guys deserve it. You've been so good that definitely you made it so far that I'm sure that you guys will understand it. Okay, so what I'm trying to say is, right, remember, so you guys do the reaction, the iodoform, the iodine. If you do it this way, right, if you do it here, the reaction will produce a species in solution. Iodine, let's see, iodine is in solution. That's why it's in equilibrium. What happens if you do it from this side? If you do it from this side, of course, the iodine will be now iodine on this side. Okay? It's also in equilibrium at some point. Why? Because eventually this iodine will become a solid. Whenever you have a result that is solid, okay, it comes out of the solution, meaning that the equilibrium gets shifted to that side. So this one that used to be an equilibrium, now since you are getting a precipitate, this equilibrium is actually shifting the reaction to this side. When you shift this reaction to this side, of course, this one is also going to get shifted to that side. So you're moving the equilibrium continuously to this side. So what happened with this guy that was in relatively stable equilibrium? It will get displaced. Why? Because you're forming here a solid. The solid always pushes the equilibrium always to that side. If this side produces a solid, it will do the same thing. But unfortunately, this side does not produce a solid because this compound is soluble. So being soluble, it will remain in solution. But since this guy has 3 iodides, it makes it so heavy that it will make it solid. This one you say like, oh, but this one has two iodides. Yes, but it's only 2 iodides. So you cannot get more iodized that, right? Because it's internal. If you have a methyl ketone, it's terminal. The terminal has the availability to produce 3 iodides. Here, no. You can have a maximum of 2. And in some cases, only 1. So this is never going to be in as a precipitate. So the precipitate formation will drive the equilibrium to that side. Okay, so that really justifies. Those are things that you guys get by experience or by looking at the molecules or from from the reactions, and that's really what favors that iodoform. In this case, bromoform, but it's a iodoform test that drives the reaction to to that methyl ketone side, right? Which is not expected. All right, so good. So now the next one is going to be the reactions that we're going to be studying, which is the main thing, I would say like the last point, your signature, right, for the I pass organic chemistry 2 is the fact that you guys are going to study these reactions, okay? So we will have different reactions. Aldol condensation, well, here you guys see aldol addition, but really the aldol addition is the first step of what we call the aldol condensation. Aldol condensation, Claisen condensation, Michael addition, and Robinson annulation, okay? So those are the 4 main reactions we're going to be learning. So far, you guys have studied already the alpha-halogenation and the iodoform test. I mean, they're both the same thing, right? Alpha-halogenation and iodoform test, they are both the same. Later, we will study alkylation, and we'll also study malonic ester synthesis and acetoacetic ester synthesis as well. But the main, and then I will put it in a table to show you how this reaction will be distributed. But those are the major reactions. Okay, so okay, so this one is the chart I was promising. Chapter 21, the main reactions. There are more reactions. I mean, just don't assume that by saying main reaction, this is it. No, there are more reactions that I already mentioned, but these are the top 4 reactions we need to study. And those are the ones that are going to be investing most of our time in this chapter. Okay, so first is the aldol. The aldol reaction. The aldol reaction can be divided into 2 phases: aldol addition, and aldol condensation. Okay, so they both use ketones and aldehydes as starting materials. Okay, so we will learn something soon about the aldol donor and aldol acceptor. Okay, but they both can be aldehydes and or ketones. Sorry, yes, aldehydes and or ketones. The product for the aldol reaction is beta hydroxycarbonyl compounds. That's for the aldol addition. And if you keep going with the reaction, you guys will form the alpha beta unsaturated carbonyl compound. Okay, don't worry about the structures yet. I mean, I will show you the structures as we study one of each, right, of each reactions. Okay, so beta hydroxycarbonyl compound is the addition, aldol addition, and the alpha beta unsaturated carbonyl compound is after aldol condensation. Okay, next one is the Claisen condensation. Claisen. Okay, in Claisen condensation, the main reactant are the esters. Okay, you guys will have 2 esters, and then the ester will condense, so forming 1,3 keto esters, or what is also called beta keto esters. Okay, it's the same thing. It's the same name for this. I mean, these 2 names for the same compound. Okay, we also will have a Claisen donor and a Claisen acceptor. Sometimes they hybridize these 2 reagents. Those 2 reactions, meaning that sometimes you can use your Claisen acceptor, and then you have a hybrid. You use aldol donor. So you guys can cross aldol donor with Claisen acceptor, and they will still give you a product. Okay, so we will see that. That's kind of like a very unusual thing. I'll try to avoid it, but unfortunately, that's what happens. That sometimes you can have hybrids of these two reactions. The one that they cannot have hybrids, I mean, for our advantage, are the next 2. Michael addition. In Michael addition, you guys are using an alpha beta unsaturated. This one is an alpha beta unsaturated compound. You have a conjugated ketone, which is an alpha beta. You can see this alpha beta because it's alpha here, beta. Alpha beta unsaturated carbonyl compound. And then you make it react with either an aldehyde and or ketone. The product for this reaction is a 1,5-dicarbonyl compound. That means that 2 carbonyls are spaced by 1,5. Okay, and the last reaction, that's when you're gonna be yelling and The smiling and laughing is when you guys make it all the way to what we call the Robinson annulation. Robinson annulation is nothing else than a cyclic aldol. Okay, a cyclic aldol because you guys are using a 1,5-dicarbonyl compound to produce an alpha-beta unsaturated. Oh, but Professor, that name sounds familiar. Yes, alpha-beta unsaturated is right here, aldol. Alpha-beta unsaturated is produced by the aldol. But what is the difference between aldol and Robinson? Is that in the Robinson, as the name says, annulation, you guys are forming a cyclic compound. Okay, an aldol is supposed to be an open chain. But if you do an aldol and the product is a ring, then you call it a Robinson annulation. Okay, so those are the steps. I mean, the 4 main reactions. We have still many more. I mean, I will put it right here. The alpha-halogenation, which also has, right, in parentheses, the iodoform inside, right? It's the same thing. We will have the alpha-alkylation. That's coming next. The malonic, with a no, malonic ester synthesis, and the acetoacetic ester synthesis. Both of them are synthesis. Okay, so they're both. So those are additional reactions we're going to study. Okay, so those are the ones we need to know the mechanism for these guys. We don't need to know the mechanism. I mean, for this one, we already know. This one, we will learn. This one, we actually don't need to know the mechanism. Okay, inside of the malonic ester and the acetoacetic ester synthesis, you guys will have decarboxylation. That's another reaction inside. But once again, we don't need to know the mechanism for these guys. Okay, only Aldol, Claisen, Michael, Robinson. Well, Robinson is an aldol, right? So then there's nothing really to do. It only makes it more complicated because you are going to start building monsters. Monsters in the sense like very big molecules will be built in Robinson annulation. Okay. And for this one, alpha halogenation, we already did it, and then the alpha alkylation. That's a piece of cake. This one is really simple, right? Okay, ready? So we are now, let's go with the aldol, the very first one. Good luck, guys. Hopefully you like it. Hey, so the first reaction. So we have the aldol addition. In the case of the aldol addition, right, in the case of the aldol reaction, you guys have a base. You can see it's an equilibrium. Do we still, Professor, you just in the very first slide, you said that the sodium hydroxide might not be basic enough to remove an alpha hydrogen. True, very true. But as you can see, the arrows is an equilibrium. So you guys want to shift the equilibrium all the way. Of course, might not be the ideal, right? You want to shift the reaction all the way to the product side. Of course, now it might not be ideal, but it works. I mean, quantitatively, if you go to the lab, I mean, it does work. Why does it work? Because the next step is the aldol condensation. And then in the aldol condensation, you guys will produce what we call an alpha-beta unsaturated carbonyl compound, which is highly stable. So the stability of the product actually drives the reaction all the way to the product side, meaning that equilibrium compensates the shift to the product side. Why? Because the product that comes next is highly stable. Since this guy is highly stable, of course, it will drag all the reaction to produce it. Okay, so in some cases, I know it sounds kind of confusing, but if we can kind of like, absorb what I'm trying to tell you is like you will really understand why some reactions are actually deviated from the expected behavior. Okay, so in this case, sodium hydroxide might not be the best base to work, but because of the product, right, the nature of the product, the stability of the product is so high, so stable, it actually drives the reaction to the product side. All right, so sodium hydroxide and water, this one is the aldol addition. You can see the beta hydroxy, you can see alpha beta hydroxy carbonyl compound. Okay. The reaction proceeds like this. We will do it by hand. You guys know that I prefer to do the reaction. Let's use another compound. You guys have acetaldehyde there. I will use, I don't know. Yeah, let's use ketone. Yeah, acetone. Okay. In the case of acetone, you guys have OH minus. OH minus attacks the alpha hydrogen. An ion, right? Carbon ion. Remember, that's what we really call the enolate. I know this is not the enolate, but It's resonance stabilized, right? And then in this case, it will attack another ketone. So this one will attack and then it will open. Okay, and of course in water, it will get protonated. And you can see that this one is the beta, right? This is the alpha position. This is the beta position, beta hydroxy. So these two compounds merge into one single compound. Now here, remember I was telling you that there's somebody that is what we call an aldol donor and an aldol acceptor. That one can be recognized in this step. Okay, if you look at this step, you can more or less can tell which one is the donor, which one is the acceptor, right? So in this case, this guy, the one that does the attack, the one that provides the lone pairs of electrons, that's what we call the aldol donor. And this one that gets attacked, right? So you see that the one that provides the carbonyl compound, that's what we call the aldol acceptor. Good. Aldol donor, aldol acceptor, always. Is it the same idea in the Claisen? Is it the same idea in the Michael? Is it the same in the Robinson? Yes, it's the same idea. Whatever provides the electrons is called the donor. Same thing as the hydrogen bond, right? Hydrogen bond donor, hydrogen bond acceptor. Yeah, the hydrogen bond donor, of course, the one that donates the hydrogen, the one that acceptor that provides the electrons. Right? I mean, it's a little bit opposite, but it's the same idea. Who gives, who receives. Hydrogen bond, who provides the hydrogen. In this case, the aldol, who does the first step, right? Who drives the reaction to the aldol, right? The aldol addition. So aldol donor. Okay. Now, there is a problem or things that we need to know for this reaction. Okay. So in this case, you will say, Professor, like here you are using the same molecule, right? And using acetone as an acceptor and acetone as an acceptor and acetone as a donor. Can I use two different carbonyl compounds? Yes, and that's the main idea. Most of the time, you don't want to make the aldol with the same compound. You want to do a cross aldol, what we call it. But there are some issues with that. Okay, so for example, if I have this acetone and I have cyclopentanone, right? What will happen in this case? What do you guys think? Well, Professor, this one is going to be the donor, and this one is going to be the acceptor. True. This one you can do it this way, donor and acceptor. What else? Can I reverse the roles? Yes, you can reverse it. This one can also behave as an acceptor, and this one behave as a donor. Professor, that makes it more difficult because I'm already having two products. It's increasing, right, my products. Professor, what about if this guy is actually behaving as a donor and as an acceptor? Without even looking at this compound. Yeah, can that happen? Yes, that can also happen. You can have a self-aldol here, okay? Cross and cross, right? Cross deals donor acceptor and acceptor donor. But you can also have the self-aldol of the acetone and also the self-aldol with the cyclopentanone. So how many products are you getting? You're getting 4 products from this combination. Okay, so let's do it. Let's do all of them. Right? So let's do the mechanism. The mechanism is pretty similar, but we'll do it with the aldol condensation. Okay, it's the next step. Okay, so let's just go to this part, right? So how to avoid that? The ways how to avoid this cross reaction is this. So remember that the donor depends on what? The donor depends on the hydrogens. Okay, so what happens with benzaldehyde, guys? Does benzaldehyde have alpha hydrogen? Well, it's an aldehyde this way, so there is no alpha. This is not an alpha hydrogen. What about here? No, there is no, because this carbon has 1, 2, 3, 4, has no hydrogen. So can benzaldehyde be a donor? No. Why? Because there is no alpha hydrogen. If there is no alpha hydrogen, it can be a donor. But can it be an acceptor? Yes, it can be an acceptor. Okay? That greatly reduces the number of products that you can produce. Okay, so one of the reasons, one of the ways is avoid, right? Avoid aldehydes or ketones that have alpha hydrogens. Okay, that's one way. Now, experimentally, there is another way how to do it. Experimentally, what you guys will do also in the lab making, right? You can incubate or you can have the hydroxide, right, or the base with one of the compounds first, one of the ketones. Let it incubate for some time, and then to that, you guys will add your second compound. So basically, you guys are making the enolate here and just waiting for the second compound to go in. So basically, it will be ready and they just click. You don't give time for this compound to self aldol, right? To do self aldol. Why? Because this one goes to the reaction vessel. As soon as it goes in, it will react. It will be caught by the ketone, right? By this acetone. This acetone will say, like, I'm ready. I'm just waiting for the other compound. Okay. So as soon as this one jumps in, right? It goes into the reaction mixture. Of course, it will react. You won't give enough time for this guy to self-react because the other guy is already waiting. Right? So that's another trick how to improve the the yield and avoid also the cross aldol. Okay, so that was the alpha beta. That's the aldol addition. Now let's continue with the aldol condensation. The aldol condensation, as we will see on this slide, let me go put it back, is that you guys have to add heat. I know that here it says acid or base, right? But since the aldol addition is done in base, right? Definitely the aldol condensation has to be continuing base. You wouldn't do it in acid. Has to be in base, and then you add heat. Okay, so both steps can be actually summarizing only one in one reaction. But let's say like this one from my previous, right? From my previous case, you guys will add more base. What am I removing? Of course, you have to remove an alpha hydrogen. Remember, the only hydrogen that is acidic here is the alpha hydrogen. This oxygen, no, because it is not. Okay, carbon ion. And here's where the magic happens. And then this is really something it's a mystery in organic chemistry. You guys recall that in the past we were always say that halogens are good living groups, right? Tosylates are good living groups. OH2 plus groups are also good living groups, but OH was never a good living group, right? So this is one of the only reactions in which you guys will see OH behaving as a living group, okay? Even with a protonation. So what happens here, according to the Aldol reaction, is that this lone pair of electron comes down here to form a double bond, and the OH leaves. That's very unusual, okay? So your product would be this compound, alpha beta unsaturated. In this case, alpha ketone, right? Because it's a ketone. And then what else? The OH minus, which is the catalyst, right? Now, many organic chemists have been discussing like why, how come, right? Why is it like this compound? Focus. Right. How come this OH behave as a good living group? Well, the reaction is mostly driven to the product side. Remember, because your compound or your product is highly stable. The resonance stabilization that you gain by forming this compound, it really supersedes any deficiency or anything that does not make sense by losing this OH as a living group. So the loss of the OH of the living group is compensated by the formation of this alpha beta unsaturated, which is highly stabilized by resonance. Okay, so the equilibrium will be shifted to the product side, forming the alpha beta unsaturated. And if this alpha beta unsaturated is a solid, it will make it even more favorable, meaning that it will be even more shifted to the product side if this guy is a solid. That's what we actually do in the experiment in the lab. In the lab, you guys will have two carbonyl compounds, and your product, which is sunscreen, right? Dibenzyl acetone, I think that's the name of the product, is a solid. So if your product is a solid, it drives the reaction even more or even faster to the product side. You shift the equilibrium to the product side, so the loss of the OH will be immediate. Okay, so you produce the alpha beta unsaturated ketone. Okay, so that's the mechanism for the aldol. So the first part, the one that I show you here, that was the first one for the aldol addition. And then from this, you continue this side to do the aldol condensation. If they ask you to do the mechanism for the aldol condensation, of course, you have to start from scratch. You cannot start from the beta hydroxy. You have to start from the basic, the very basic, and then continue until you make it to the alpha beta unsaturated. All right? Okay, great. So now, Professor, how do I do now with the mechanism? How do I come up with a product, right? So I want to know the alpha beta unsaturated, but I don't really want to go through the tedious part of writing the mechanism. Yeah, that's an easy task. So for example, they tell me, Professor, I want to know what is the aldol condensation product between this ketone and this ketone, these two. You ask me like, I want to know the aldol condensation. Okay, and then I will answer you this way. Okay, so both compounds, both ketones can be donors and acceptors. This one has alpha hydrogens, therefore it can be a donor. This one has alpha hydrogens, therefore it can be a donor. They are both ketones, therefore they can be acceptors. This can also be acceptor. So you can have a different array of products. Self, aldol, self-aldol, and also donor-acceptor, acceptor-donor. So technically, you can have 4 products here. Let's do one by one, okay? Let's do first the self-aldol of this, self-aldol. So you want to do the self-aldol, the thing that you guys have to do is make phase, right? You guys are going to phase the alpha hydrogen with the COO. Make it phase. Okay? The alpha hydrogen that is going to be forming the aldol, you're going to make it phase with the ketone. And then after that, what are you going to do? Erase the COO, and you guys are going to make a double bond there. That's your aldol. That's it. Okay? Your donor, make it, expose the alpha hydrogen of the donor, and then the ketone, right, the next one, the acceptor, will expose the COO to that alpha hydrogen. And then it will alpha carbon, and then just close it with a double bond. Now it's like, let's do the self-aldol of this guy. Okay, you want to do the self-aldol of that, it would be this one, right? This is this compound. And now my alpha hydrogen for that, I will make it close to the COO of the same compound. So what is next? Erase the COO and instead make it a double bond. That's my second compound. Okay, you want to draw it nicer. That is 1 and 2. That's the self-aldol of this guy. That's the self-aldol of this guy. Now you want me to do, I want, Professor, donor acceptor. Okay, donor. Donor means that it's going to contribute with the alpha carbon. Acceptor means that it's going to lose the COO. Okay, let's do it. Exposes the alpha hydrogen, the other one loses the COO. Okay, what happens? Erase the COO and draw a double bond instead. And that's your second product. I did this one. Now let's do this one. Acceptor, donor. Donor exposes the alpha hydrogen. The acceptor loses the COO. Loses the COO? Okay, lose it. And that's my 4 product. Okay. So if they ask me like, what are the 4 aldol condensation products from these 2 ketones? Well, that's the self-aldol, and the 2 cross-aldols. Okay. Great. Now, let's do one example in which we are actually using compounds that don't have alpha hydrogens. Okay, let's use benzaldehyde. Benzaldehyde is the one that we were discussing before. There are many more. I mean, benzaldehyde is not the only one. Let's do benzaldehyde with what do you guys want? Pentanone. 1, 2, 3, 4, 5. Okay, pentanone here. Okay, now you have to, if they ask you, draw all the aldol products, aldol condensation products. Okay, so to do the condensation products, you guys have to look at the molecules and then analyze it, right? So can it be a donor? No, no alpha hydrogen, so it cannot be a donor. Can it be an acceptor? Yes, it's an aldehyde. Aldehydes are, by nature, they are acceptors. This one is a ketone, can also be an acceptor. Can it be a donor? Yes, because it has alpha hydrogen, so it can be a donor. So the only way you guys can do is like donor acceptor, this combination. That's the only one that you can make. What about the self-aldol here? Can I do self-aldol with the benzaldehyde? No, because benzaldehyde can never behave as a donor. What about the pentanone, 3-pentanone? Yes, that one can be self-aldol. So this one can do it. Okay, so let's start with that one. So how many products can you make? You can only make 2 products. Donor acceptor and then the self-aldol. Okay, so let's do the self-aldol first. That one, that's a donor. And then to that, I will expose the other C double O. Remember, you have to erase this C double O. And instead, you guys will replace it with a double bond. Ta-da! That's my compound. That's this one. Now let's do the donor acceptor. So you guys want donor acceptor. And then to the alpha hydrogen, this one, I will expose the aldehyde. Okay. Replace that C double O because that's the acceptor, and then put a double bond instead. And those are your 2 products, aldol products. Okay, make sense? Okay, so that's how you guys save time instead of writing the whole mechanism to come up with the aldol product. Okay, now that's not the only question that you guys will be asked. It's not only drawing the aldol products. You will also be given an aldol product, and then they might ask you degrade it or decompose it or predict which ones are the aldehydes and or ketones, right, that produce this particular aldol. Okay, let's do it. I show you. Okay, they ask me what are the aldehydes and ketones that created this aldol. First you have to recognize that it's an aldol. Can I see that it's an aldol? Yes. Why? Because it's alpha beta unsaturated. Alpha beta unsaturated are automatically aldol compounds. Okay, so I can see the alpha beta is alpha beta unsaturated carbonyl compounds. It's an aldol. Now, what you guys will do is do the reverse. Now you guys will break the double bond. Break the double bond, and you guys will separate it. Okay, you separate it, and then to the side that has the ketone, you guys will leave it intact. Don't do anything. Okay, that one, this side. Don't do anything. What about to the other side? The other side that has no double O, you guys will actually replace that double bond with a double O. And that's it. Those are my 2 carbonyl compounds that generated this aldol. Another one, of course. Okay, this one. Okay, so first is it an aldol? Yes, it's an aldol. Why? Because it's an alpha beta saturated carbonyl compound. So break the double bond, right? And separate it. To the side that has the carbonyl, do nothing. So that means that you guys will have this compound, right? Remember, this carbon stays there. And what about to the other side? Well, to the other side that has no carbonyl, then just put a C double O instead. And this one, of course, is a hydrogen, right? So 1, 2, 3, 4. 1, 2, 3, 4. And those are my 2 carbonyl compounds. Okay? Always breaking at the double bond. One small one that is able to fit here. Same thing. Let's break it at the double bond, right? Break it. So to this side that has the, right, the oxygen, to nothing. 1, 2, 3, 4, 5, okay. And the C double in the middle. And the other side that has no double O, right? What happens to this one? Well, just complete it with a double O, right? 1, 2, 3, and then that 3 is going to have a double O. Aldehyde. Why aldehyde? Because here it has a hydrogen that I don't see it, but it's there. So that's why this hydrogen is this hydrogen. And then 1, 2, 3, 1, 2, 3, and those are the two compounds that generated this compound by aldol condensation. Okay, always under the idea of aldol donor and aldol acceptor. Okay, see how is it? Do you guys like aldol reaction? Yeah, hopefully. Yeah, let's see the next slide. We're moving. I mean, I know that is the last one. I know that you guys want this video to be short, so I'm trying to condense. I mean, giving you all the information that is needed, but at the same time, I respect that, you know, that you want to be done, right? We're towards the end of the semester, so we want to take full advantage of the time for this particular recording. All right, so that's the reaction. The mechanism should come next, right? The aldol addition, aldol condensation. Remember, it is a two-step reaction, but they can easily be merged into one single mechanism. Okay, so whenever you are being asked to do the aldol condensation, make sure that your aldol addition is an intermediate. You have to show it. Okay, so when you're asked from aldol condensation, don't start from this. No, if you do aldol condensation, you guys should start from this too, and then go all the way to the alpha beta saturated compound. Okay. Oh yeah, that's something I forgot to mention, that whenever you guys produce an alkene, right, which is the main thing that you're producing, an double bond, we should respect the aesthetic hindrance, right? So you might have two options, two alternatives. Should I produce alpha beta unsaturated trans or cis? Of course, all this last semester and this semester, we've been always using aesthetic hindrance as a major, right, deciding, right, rule to produce it. And we always know that the trans, right, the trans product is more stable because minimizes steric repulsions. Okay, so in this case, the major product would be the trans alpha beta unsaturated, but the cis alpha beta unsaturated should also be produced, but in way smaller scales. Okay, minor product. Good. This one is the cross aldol I was telling you. Well, here they're not showing you the cross aldols. They're showing you the cross beta hydroxy, right? But it's the same thing, right? So you guys can use this guy in red, right? That one is acceptor donor. The blue is acceptor donor. Here, the red is the acceptor, the blue is the donor, and in the last case, the blue is the acceptor and the red is the donor, right? So you have different combinations. Only as long as you guys have alpha hydrogens. Remember, analyzing alpha hydrogens definitely makes a big difference, right? So in this case, you can use formaldehyde, right? Formaldehyde has no alpha hydrogens. If it has no alpha hydrogens, so it can only be an acceptor. It cannot be a donor. This one is propanol. Propanol has alpha hydrogens. Therefore, it can be a donor and can also be an acceptor. In this case, they're doing a cross aldol, meaning that they are using the formaldehyde as an acceptor and the propanol as a donor. And that's how you get this particular product. But Professor, can I also do self-aldol with propanol? Yes, you can also do self-aldol with propanol. Okay, so that's another option. Benzaldehyde was another one that I showed you, right, a few minutes ago. The benzaldehyde is another carbonyl compound, an aldehyde that has no alpha hydrogens. Therefore, it will be very minimum, right, the number of aldol products that you will get. Okay, retrosynthetic analysis, that's how you break it. I'll show you already how to break, the aldol compounds, right? So let's go to the next one, Claisen. Claisen condensation, you guys are gonna, it's very similar to are very similar to Aldol because the concept is the same. So meaning that you guys have a donor and you have an acceptor, but now the base is changing a little bit. And also the starting material, right? So Claisen condensation, Claisen, which is the last name of a scientist, he actually thought that it can only be applied to esters. So like if Aldol, this guy, Aldol came up with a reaction between aldehydes and ketones, he explored the option of esters also to be used as a donor and acceptor. And then that's how he came up with this Claisen condensation. Okay, so ester, you can see here the ester, here is an ethyl ester. Therefore, your base has to be also an ethyl. If this guy is a methyl, then you will use methoxide. If this guy is a terbutyl, you will use terbutoxide, right? So the ester should always be conjugated or should always be identical to the base that you are using, okay? For why? Why, Professor? Because you might have some transesterification problems. You will lose the ester if you don't use the same one, okay? That's step number one, and step number two, you guys have to protonate it. So the product is a beta keto ester. So this one will be, this is the ester, you see this is the ester, this is the alpha and the beta. So that's why it's called beta keto ester, right? 75%. It's a high yield. So that's the mechanism. Okay, so let's do it by hand, the mechanism, Claisen condensation. Okay, so let's use, okay, this ester. Well, let's change the ester. I don't like ethyl, let's say. I want methyl. Methyl ester. Okay, if it's methyl ester, you guys have to change your base. Now you're gonna use methoxide. So methoxide is a strong base. So the strong base is going to deprotonate, right? The alpha hydrogen. So it will deprotonate it, gets the carbon ion. Okay, so this one is what we call the Claisen donor. And it will attack another ester. Of course, where is it going to attack it? It's going to attack it at the COO. Okay. Attacks, pushes the double O. Okay. What happens with this, with the acceptor? Of course, the acceptor will be O minus, and this guy will come in. That one's going to be a little difficult to show, but this is this. Okay, 1, 2, 1, 2, and the other side should be the ester. Okay. Then this guy is gonna come down, and then it will lose the methoxy as right, as a leaving group. It's 3, right? 1, 2, 3, 1, 2. Oh, I'm missing here a carbon. Yes. Yeah. I was missing a carbon. So it comes down. Yeah. 1, 2, 3. 1, 2, 3. COO. Yes. After that, it comes this guy, and this guy has 2. Yeah. Yeah. These 2 in red are these 2 in red, right? And that's the ester. You got it. Okay, so that's the Claisen condensation. You guys can see that there's a 1,3 keto ester. Keto, right? Keto or beta keto ester. This is the alpha. This is the beta, respect to the ester. So that's how you made the Claisen condensation. That's the mechanism, actually. But now, so something very important is that there's a hydrogen here. This hydrogen, right, will be exposed to another methoxy because you have excess of methoxy. So methoxy will remove that hydrogen. And you guys will have an ion. This is very important, and this is really the driving force for the Claisen condensation, is that you guys are producing an anion that is resonance stabilized. That's really what shifts the equilibrium all the way to this side, because even though I draw one arrow only, but this equilibrium, these are all in equilibrium. And to drive this to the product side is this stabilization. Nobody here is stabilized by resonance. Nobody, nobody, nobody. Nothing is stabilized by resonance. Only the product. So by the product, by being stabilized by resonance, it shifts the equilibrium more to the product side. Why? Because of course the equilibrium says like this guy is more stable than us. So therefore, let's make some room to produce this compound. And in the second step, right, according to the reaction, you guys are adding acid. Of course, in the second step, you guys will protonate it. That's the final product. Okay, but it is like this, the Claisen condensation. The protonation of the alpha hydrogen with the methoxy, it creates the carbon ion, which is the Claisen donor. Okay? The Claisen donor will attack the Claisen acceptor and the COO. The COO will open up, right? Now from an sp2 carbon, we'll go to an sp3 carbon, but then that is only momentarily, right? It's just like very brief lifetime for that species. So this one will come back down and they will lose that methoxy, minus methoxy, right? Loses the methoxy, loses it, and then recovers the COO. That recovers COO is the COO. Okay, see, 1, 2, 3, COO, 1, 2, 3, COO. Yeah, and this carbon is here. You have 2 carbons and then the other methoxy, the other ester. This methoxy then removes the hydrogen. That's really the deciding step because that's highly stabilized by resonance. Resonance this way, resonance this way. But then in step number 2, you protonate it because you cannot keep it negatively charged all the time. So it will protonate it and then take you to the neutral form, right? So that's introduce you to the Claisen condensation. Great. Okay. All right. Great. So let's go back to the slides. Okay, that's the mechanism. You see, you open the from sp2, from the sp2, now you go to the sp3, you return, right, the bonds, and then you lose the methoxy. The methoxy then deprotonates, and that's the species that is stabilized by resonance. Okay, so that's what we call a beta keto ester. Beta, you can see the beta keto ester is produced in a Claisen product. In the second step, you guys are protonated acid. That's how you recover neutrality. Okay, now let's do the analysis for the Claisen. So in the case of the Claisen, very similar analysis, right? Or how to make it, right? Same. Let's do the same thing we did with the Aldol. How to make a Claisen without going through the entire mechanism. Okay, so let's say that you are given this particular ester, right? Oh, that's something very important. I forgot that the ester should have 2 alpha hydrogens. That's very important. If not, you cannot make the Claisen. Why, Professor? Why? Because remember that the Claisen involves the formation of this anion. If you're not able to make this anion, then there is no Claisen because there is no stabilization. What are those 2 H's, Professor? Okay, the 2 H's are right here. This is blue H and this is red H. You have to lose 2 hydrogens. So you need to have 2 alpha hydrogens in the ester to be able to do the Claisen. If you don't have those, you can't do Claisen because it's not stable enough. Okay, 2 alpha hydrogens. So here, for example, this ester, I can see it has 2 alpha hydrogens. Perfect. It can do the Claisen. Okay, so let's do the Claisen between that with itself. Let's do it as self-Claisen. So the self-Claisen you guys will do, you will do the same thing. You will expose the Claisen, the alpha hydrogen Claisen, and you guys will expose it to the ester, but the COO side. Okay, so for example, the Claisen used to be that's the same Claisen. But I will expose the alpha hydrogen from one to the COO of the other one. Now, what should I do? You guys are going to lose the ester, okay? Lose this guy. And you guys will connect it with the alpha side. And that's it. Of course, it looks bad, right? But if you redraw it, right? Here, and then here, another C double O. Right? Let me see. This is this. 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 Yeah, done. That's the Claisen. Right? That's how you guys, right? That's how we are going to make a Claisen without going through the mechanism. Now let's do a cross Claisen. Okay, let's do a cross Claisen. Right, that one has two alpha hydrogens, and then another ester. Professor, can I do with ethoxy? Yeah, you can do it with this, right? Two esters. Now you select, Professor, can this be the donor? Yes, this can be the donor. Can this be the acceptor? Yes, can be the acceptor because it has a C double O. So C double O is, well, C double is an ester. To be an ester can be a Claisen acceptor. Has to be an ester to be a Claisen acceptor. So this one is a donor because it has alpha hydrogen. So really, a Claisen donor, a formal Claisen donor has to be an ester. But can it be also a ketone and an aldehyde? Actually, yes. Okay. It can also be that's how you get the hybrid by having the ketone ester, because you can have an Claisen reaction. In that case, the aldol has to be the donor and a Claisen is the acceptor. That's how you match them. Can I do the opposite? The ester as a donor and the aldol as an acceptor? Yeah, but that one wouldn't be a Claisen. That would be, no, I don't know. That something comes up, maybe, but I mean, no, in that case, no, because the esters are less acidic than ketones. So you guys will reverse it. It will reverse the donor acceptor. No, it wouldn't work. It wouldn't work. Right? Let's go back to this point. Okay? So sorry, I was just thinking out loud. So but yeah, you can have hybrids. But for this class, I mean, we will keep it formal. Okay. But if you guys see something, in the references, in the books, in the internet, yeah, sometimes you can hybridize Aldol and Claisen, right? But let's do in our class, we're going to be doing a formal Claisen and a formal Aldol. Right? So here in this case, you guys have two esters. This one has two hydrogens here, so it can be a donor. This one has two hydrogens here, so it can be a donor. They're both esters. That means that they can be both acceptors. Okay, so let's make this one work as a donor with itself. Let's do the self Claisen. Okay, I'm gonna make face the alpha to the carbonyl of the same compound. Okay? So remember, I will trace a single bond here and erase the ester of the acceptor, right? In this case, this is the acceptor. That's the first one. Yeah, that's it. That's my first Claisen. Second one, I want this one as the self Claisen. Okay. A little bit longer, but then it's only the same thing. It's only with the, okay. 1, 2, 3, 4, 1, 2, 3, 4. Yes. So make a single bond and erase this ester. That's it. The product would be 1, 2, 3, 4, 1, 2, 3, 4. Here, 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Yeah, that's the product. Now the cross Claisen. Okay, let me make this as a donor and this one's an acceptor. The donor exposes the alpha hydrogen and the acceptor exposes the C double O. Okay, then what should I do? Connect it and erase the ester. Then just reorganize. Okay, there is one more, right? Yeah, let's do it. Don't have a space. Yeah, no, this was new sheet. Yeah, now in this case, I will be using this one as a donor and this one as an acceptor. If this one is a donor, it will expose the alpha hydrogen side, right? So it would be ethyl, oxygen. Okay, it will expose this side, and then this one will expose the COO side. Yeah. Okay. Make the connection, ping, and erase the ethyl, the ester. Redraw it to make it look nicer. 1, 2, 3, 4. Dun, 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 dun. Yes, that's it. Right? 1, 2, 1, 2. Yeah, perfect final product. So those are my four. Let's put it here. The four Claisen products, right? They all, I mean, they all look similar, but they are actually different. Okay. So the same way we can do a Claisen, to put together a Claisen, you can also break apart a Claisen, right? So to break apart a Claisen, right? For example, methoxy, they ask me now in this case, I want you to break this ester apart. Okay, so if you want to break the ester apart, the Claisen apart, so you guys have to number the 1, 3. So it would be 1, 2, 3. Okay, so when you have the Claisen, right, you are gonna break it between carbons 2 and 3. 2, 3 is the where you guys are gonna cleave it. Okay, cleave it. So what should you start numbering? You should start numbering on the ester. So with the ester, 1, 2, 3. So cleave it in 2 and 3. 2, 3. For Claisen, break it 2, 3. Okay, slash. Okay, so once you break it, cover it. So to the ester side, this one is the ester side, do nothing. So the ester will do nothing. So meaning that the first one would be, it still keeps number 2, but that's nothing, right? And then to the other part, right? You see the 3. The 3 has now just an open double O, C double O. So complete it with an ester, right? That's what is missing, this part, right? You look at it. So complete with an ester. That's it. What ester? Methyl, methyl, methyl. Remember that both esters should match. You cannot have a methyl ethyl or methyl isopropyl, no. Or methyl cyclobutanol, no, you cannot. So it has to be exactly the same type of ester. Good. Another one, let me see. Yeah. Okay, so they tell me, do the retroclassing of here. So come up with two, the two starting materials that created this Claisen. First, I have to recognize that I'm in front of a Claisen. How do I know I'm in front of a Claisen? Because it's a beta keto ester. What is the beta keto ester? It's here. Beta keto ester. It's a beta keto, right? Can I mistaken this with an aldol? No way. You cannot do an aldol because remember, aldol is an alpha beta unsaturated. I don't see a C double C here, so it cannot be an aldol. Don't try to look for an aldol here because remember, the aldol is a C double C, it's an alpha beta unsaturated. This is an aldol. This is a Claisen. Right? So beta keto ester. I need to see an ester. I don't see ester here. There is no way you can have a Claisen here. Right? So here. So then what should I do? Remember, Claisen, you break it between 2 and 3. Okay, start numbering. The ester gets number 1. I number it. So cleave it between 2 and 3. To the side that has no ester, right? I cleaved it, right? I have a C double O, open C double O, then complete it with an ester, right? So the double O side that is close to the cleavage, then you complete with an ester. In this case, ethyl ester. Too harsh. I'm too happy teaching this. Okay? And next, this side, just do nothing, right? We said to the 2 side, do nothing. So meaning OAT. See, same thing. And those could be your 2 starting materials for the Claisen. Okay, good, makes sense. I mean, yeah, I mean, as I said before, so this part, this particular, the next reactions, they all have the same concept. Okay, so I know that there are different reactions because Claisen is not the same thing as an aldol. And of course, the next one, which is Michael is not going to be the same thing as a Claisen or as an aldol, but they share many things in common. Like for example, the carbon ion, the donor idea, the acceptor idea, right? The mechanism, for the formation of a compound that is either conjugated or a, conjugated ketone, right? Because this is kind of like conjugated ketone. It's the same concept, right? All right, so let's continue now with the slides to see what is coming next. Next, I believe, is the alkylation. This is a parenthesis, right? Remember that at some point I told you guys, right, that you have some, right? So far, we did the Aldol already. We just finished the Claisen. We still have to do the Michael and the Robinson, but also there were two items. So we did the alpha-halogenation, and now we're about to do the alpha-alkylation. Okay, so now it's coming the alpha-alkylation. So we have few things, right, pending, but now is the time for the alpha-alkylation. So in the alpha-alkylation, what we're gonna do is you're gonna be alkylating the alpha position, right? So we're gonna be alkylating this ketone, right? So you guys can alkylate it this way or you can alkylate it this way. Can I do this selectively? Professor, before you say that you always form the enol or the enolate that is the most attituted. So technically we can only alkylate here. Is that true? No, depends. Depends on the base. You can alkylate different positions. That's the beauty of organic chemistry, that you can use something which is called steady hindrance to favor one particular alkylation site. Okay, so that's what is coming next. Okay, so now next is coming how to decide which side to alkylate. Right. So in this slide, we guys have the right the alkylation, right? So you guys can see here we have cyclohexanone. Here, the advantage is that this particular ketone is symmetrical, meaning that it has the same substitution. So this one is primary. So there's really no big deal. There is no difference. So in this case, they're using LDA. I introduce you guys to LDA. LDA will deprotonate it and then will alkylate it and listen to a style, right? So that's the idea. But you guys have two ways, right? So what if I don't want the most attituted? I want the least attituted. So that's why we call it thermodynamically controlled and kinetically controlled, or kinetic enolate or thermodynamic enolate. The kinetic enolate is the one that is the least substituted carbon, and the thermodynamic is the most substituted carbon. So how do I modulate that? So you guys are going to be using different types of base. For example, if I want to target the least attituted, I have to use a bulky base. Why? Why? Because the bulky base will not be able to enter to the crowded side, right? LDA is too big. It won't be able to access, right, this particular carbon. So the LDA, at low temperature, you guys will only have access to the least attituted. What happened with sodium hydride? Hydride is very tiny. It's tiny, teeny tiny. So hydride will be so small that it's able to deprotonate this side. And then that's why it can access the most secluded, right, carbon alpha hydrogen. Okay, so let me show you what happens on the paper. Okay? So let's say that I was showing you this particular pentanone, 2-pentanone. Right? You guys use LDA at low temperature. Okay, the LDA at low temperature, what it's going to do, LDA is so bulky that it's not going to access this one. You will say, like, Professor, but this one should be the most stable. Yes, it's the most stable, but LDA is so big that it will be very difficult to access this hydrogen. It will be easier to access this hydrogen. Okay, so it will access then this particular, giving you this carbon ion as the major product. Why? Because of the size of LDA. And then you continue the reaction by mixing it with maybe ethyl chloride. Carbon ions are good nucleophiles. Therefore, they will attack this carbon and this one will leave. So therefore, it will give you this particular compound. Okay, you alkylated it. See the ethyl? This ethyl is this ethyl. And this carbon is the one that attacked, right? Is this carbon. That's with LDA. That's why they call it kinetic kinetic enolate or the kinetic product. What about in the other case? Like, let's use, I want to use now hydride instead at high temperature. Then it's thermodynamic. So the hydride is so small that it can access the most secluded hydrogen. So it will give you this carbon ion. So this carbon ion then attacks an ethyl chloride, right? And this one will attack, and this one leaves. So your product would be with an ethyl, right? So the ethyl now gets added, right, or gets inserted to the alpha side, but the other alpha side, because hydride is very small, so it will access this one that is kind of hidden, right? Is the inside. It's very internal hydrogen. So the only way I can remove an internal hydrogen is by using a smaller base. If you want to remove the more exposed hydrogen, you have to use a bulky base, because the bulky base is the only one that will be able to selectively withdraw, right, or to take away that hydrogen that is mostly exposed. Okay, so that's really the difference. That's the alpha-alkylation. Very simple, right? So it's this one is an SN2 reaction. Remember, this is an SN2. Therefore, you guys need to do the less substituted alkyl halide. Okay. Okay, so now that we know about alkylation, I think that's the opportunity for us to study now. It's either the Michael or no, it should be the malonic ester synthesis, right? So let's see what comes next. Yes, the malonic ester synthesis. Those are the next two. Malonic ester synthesis, and then comes the acetoacetic ester synthesis. So what are the purpose of these two? So the purpose is, like, at least for the malonic ester synthesis, you guys will be able to make carboxylic acids. Carboxylic acid, okay? So carboxylic acid, substituted acetic acids, carboxylic acids. And what about the acetoacetic ester? So acetoacetic ester synthesis, you guys will make methyl ketones. Okay, how does that work, professor? Okay, it works like this. Okay, so we will work with malonic ester. Malonic ester is a diester. This one is called the malonic ester. That's going to be your substrate. That's going to be your starting material. This one, as you see, that one has an alpha hydrogen. Let me change color. I don't like this. Right. And yeah. Always. Okay, this alpha hydrogen. So the alpha hydrogen is going to be removed with ethoxide. Yeah, we know that this diester, of course, the diester is more acidic, so the ethoxide will remove it, getting this particular anion. Now, this anion, according to what we just studied, the alkylation, it can react with an alkyl group, and this one will allow us to tailor. You guys will design your own carboxylic acid. So if I want a pentanoic acid, okay, just measure it, think of it as design it. What type of alkyl halide do I need to make pentanoic acid, let's say, right? What type of alkyl halide do I need to make, maybe like a butanoic or hexanoic or heptanoic acid, right? So you guys will design it. After that, you guys will do a hydrolysis, H3O plus in heat. That one we studied on the previous chapter, chapter 20. On chapter 20, acid and heat, you guys will hydrolyze. Ester and ester, they get hydrolyzed to carboxylic acids. Okay, 2 carboxylic acids. Then next, you guys will apply heat. What happens with heat? With heat happens something known as decarboxylation. How can I decarboxylate this dicarboxylic acid? Because if you guys have a carboxylic acid that is beta respect to a carbonyl compound, it will get decarboxylated. Okay, so for example, alpha beta respect to a carbonyl. But you say, like, professor, but the beta is actually another carboxyl group. Yeah, it is a carboxyl, but it doesn't matter. As long as the carboxylic acid, any carboxylic acid, is beta respect to any other COO, it will get decarboxylated in the presence of heat. That only happens with heat. Okay, so carboxyl with heat, it will get decarboxylated. You guys will have to show, don't forget, show the COO, because that's the only way how you can prove that you are decarboxylating. So COO has to be present. And then you guys lose the carboxyl group. The carboxyl group is lost. Then you are left with your carboxylic acid. See? So you guys will get the skeleton of the, let me change the color. This particular region comes from the malonic ester. So you guys have to think of what type of, right, alkyl halide you have to add to decide, right? So it's the carboxyl plus one more carbon is what you get from the malonic ester. Okay, now let's do it by hand, because I know that from the slides might not be enough, right? So let's do the scratch, right? The malonic. We're not doing the mechanism. Remember, for malonic ester and the acetoacetic ester, no mechanism. We only need to do the rationale behind it. So you guys will have the malonic ester. In the malonic ester, you guys will start by adding the ethoxide, which is the base. The base will deprotonate this hydrogen, like this hydrogen, because that's the most acidic. You guys will get the anion, which is the enolate, right? The enolate anion. That enolate will get alkylated. Let's alkylate it with what? With, yeah, chloride. Butyl chloride, right? I'm putting a butyl. 1, 2, 3, 4. Butyl chloride will get alkylated on this position. 4, right? 1, 2, 3, 4. Okay, 1, 2, 3, 4. Good. I added it. Now is H3O plus heat, right? It will hydrolyze. The esters will be gone. 1, 2, 3, 4. Okay. And then I apply more heat or high heat, right? Double heat. And then here's where occurs the decarboxylation. So this carboxyl group is beta respect to another carbonyl. This is alpha beta. So it's beta carbonyl carboxyl group. It gets decarboxylated in heat. So this group will disappear. What is left? 1, 2, 3, 4, 5, 6. Hexanoic acid. 1, 2, 3, 4, 5, 6. Okay, good. So you produce hexanoic acid and carbon dioxide. Make sure that you guys put carbon dioxide, because that's the proof of the decarboxylation. Okay, so that's how you make carboxylic acid, and you design it. What if I, instead of butyl, I put ethyl? Well, you make this change order. What if I put branches? Well, this carboxylic acid will have branches, right? So you design it. Basically, with this alkyl halide gives you really, it opens a world for your creativity to design your, right, your carboxylic acid. But remember that always these two first come from the malonic ester. These two are malonic ester. Does that mean, Professor, that I cannot make benzoic acid? Yes, you cannot make benzoic acid. Can you make benzylic carboxylic benzylic acid? Yes, that one you can. But actually, no. Let me think. No, you cannot. Yeah. You cannot make the benzylic. Right? I mean, if you ask me, like, can I make this one? You actually cannot, right? Because to do this acid, right? This one comes from the malonic ester, and this one comes from the alkyl halide. But we know that phenols are not alkyl halides, so you cannot do this substitution, right? It needs to be an sp3 carbon, and this carbon is not sp3. Okay. Okay, then let's use the malonic ester. They tell me, okay, I want you to make this carboxyl group. Okay, I want you to make this carboxyl, right? This carboxylic acid. Okay, if you want me to make a carboxylic acid, well, first, remember that the carboxylic acid and the first carbon, they come from the malonic ester. This one. And the next one comes from the alkyl halide, the next part. So the alkyl halide, what was your alkyl halide? Is 1, 2, 3, 4. 1, 2, 3, 4. And then that has the halide. And of course, the other one was the malonic ester. If you do it, you will notice that definitely it will come from the malonic ester. Okay, so another example, I want you to make this one, this carboxylic acid. Okay, you want to make this carboxylic acid, well, remember that the first two carbons, right, carboxylic carbon and the first carbon will come from the malonic ester. What about the rest? Yes, the rest can come from the alkyl halide. Is this an alkyl halide? Yes. Can it be an alkyl halide? Yes. So it will be a cyclopentyl halide. Okay. Good. Now in the alkylation, I also forgot something that you can do, and you will see in some of the old exams and all, right, old quizzes. Sometimes you can use a dihalide, right? So for example, you have the malonic ester. You use the base, right, which is ethoxide in this case, right? Ethoxide will get it the carbon ion. But in this case, instead of using a single alkyl halide, you guys will use a dihalide. Maybe one more. Okay, so what happens here? When you do this reaction, of course, one bromide will be attacked, but the other bromide will be open. Okay, so what happens here? Ping, 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 ping. 1, 2, 3, 4. 1, 2, 3, 4, bromide, right? 1, 2, 3, 4, bromide, 1, 2, 3, 4, bromide. Then here, again, you're going to be using ethoxide. What's going to happen with ethoxide? It will deprotonate the second hydrogen. So it will give you ethoxide. One, two, three, four. And they will form the carbon ion. Now this carbon ion can again attack the bromide. The second bromide, of course. Now you will form a ring. Let me put it higher because it won't have enough room. It will be 1, 2, 3, 4. No, I thought I had 4 carbons. 1, 2, 3, 4. 1, 2, 3. Oh, I'm missing one. Mm -hmm. 1, 2, 3, 4, 5. Good. Okay. It's a cyclic compound. It's a cyclic compound, but you have to use a dihalide. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cyclic, right? And then after that, of course, you use the acid and heat, right, to hydrolyze. And then you use extra heat, more heat, and then it will decarboxylate. You lose one carboxyl group. So what are you left with? You are left with the carbon dioxide, of course, and C double O. Yeah, that's it, right? Because this is gone. Cyclohexyl carboxylate, right? Carboxyl. Cyclopentyl, my bad. Okay, that's another one. I mean, I didn't show it. I mean, but you guys will see that's another option. How to make another type of carboxylic acid. Technically, you can design your carboxylic acid, right? So, but remember that the first two, they will have to come. So this is what the beauty of this. Remember, always the first two, right? The first two are from the malonic ester. That means that the rest comes from the halide. So that means that you guys have 1, 2, 3, 4 high halide, right? Dihalide, because they're both connected to the, right? To the malonic skeleton or the backbone. So that's how you can predict that it came from a dihalide. Okay, good. So that's the malonic ester. The acetoacetic ester is very similar. Acetoacetic ester. The acetoacetic ester, you guys will use this compound. Okay, this one. This one is the acetoacetic ester. Okay, you will exactly do the same procedure. You guys will use ethoxide. Ethoxide will deprotonate the hydrogen, produce the carbon ion enolate. This carbon ion enolate can attack an alkyl halide. Don't worry about the mechanism. I'm just doing it for me to as I show you what happens, but we don't have to. Okay, 1, 2, 3, 1, 2, 3. Right. After that, hydrolysis, H3O plus and heat. That one will hydrolyze the ester. The ketone, nothing. Remember, ketones, they don't get hydrolyzed. Okay, 3. And after that, I apply more heat. Right? This is the decarboxylation. This carboxyl is better respect to this ketone, right? 1, 2, 3. So it will get decarboxylated. So you get carbon dioxide plus, now this is gone, I will get 1, 2, 3, 4, 5, 6. Methyl ketone. Okay, so that's the main goal of the acetoacetic ester, is that you guys are going to make methyl ketones. That's the whole point. In the case of the methyl ketone, right? So the first 3 carbons are going to come from the acetoacetic ester, and the rest will come from the alkyl halide. Okay, makes sense? Okay, good. So let's do one more example, right? So for example, they tell me like this particular methyl, yeah, this guy. How do you synthesize this particular compound? Okay, it's a methyl ketone. So technically, methyl ketones can be synthesized by the acetoacetic ester synthesis. So 1, 2, 3, the first 3 of the ketone, including the methyl, they will come from the acetoacetic ester. What about the rest? The rest will be the alkyl halide. Okay, so how is this alkyl halide? Like this. That's the alkyl halide that you use for this acetoacetic ester synthesis. And this backbone, of course, I have to use that plus the acetoacetic. Okay, if you combine these two, you will get this particular methyl ketone. But that's how you recognize, right? So 1, 2, 3, and then that's what you need for, right, to identify the 2 precursors for this acetoacetic ester. Right? One more. Okay, yeah, I have the back of this sheet to do another one. Can I also do a ring, Professor, the one that you showed before? Yes, of course. Let's say you have this. This is still a methyl ketone, but you will tell me, Professor, now how do I do? Well, remember, for methyl ketones, is the first 3 carbons, 1, 2, 3. So these 3 have to be taken. So what is the other alkyl halide? Well, my alkyl halide would be these guys. But these guys are connected to the same carbon. Okay, well, that means that you have a dihalide. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then they are both connected. That means that this one used to be a bromine, and this one also used to be a bromine. Right? That's the only way how you can connect them. They're connected to the same carbon. So that means that they're connected to the same carbon. They're both reactive. Both ends have to be reactive. If it's an open chain, no. In the previous case, we had an open chain. So they are not cyclic. The halide is not a dihalide. But this one, there's a cyclic methyl ketone. So therefore, it has to be a dihalide. Right? One more. Okay. Is this also the same thing? No, this is not the same thing. Why? Because it's 1, 2, 3, 1, 2, 3. That's the acetoacetic ester, and the rest is the halide. So yeah, that's totally different story, right? 6, this is this carbon, and then of course this one is the halide. And the acetoacetic ester, right? You always need the acetoacetic ester. No mechanism for this. Only the way how to synthesize it. All right. Okay. So next is gonna be, now we're gonna go to the Michael. Well, now let's cross it, right? We cross it. Yeah. We done. Done with malonic ester. Done with acetoacetic ester. Now we have 2 steps missing. Okay. So the Michael addition and the Robinson annulation. Okay, so before we go to the Michael addition, let's just see what's missing from the, the acetoacetic ester synthesis. Yeah, I mean, we went over already, right? The acetoacetic ester synthesis is for methyl ketones, whereas the malonic ester is for carboxylic acids. Okay, well, we're ready now for the Michael addition. It's the second to last reaction that is going to be covered in this chapter and also in the course. So enjoy it. So in the Michael addition, you guys have the reaction between an alpha beta unsaturated compound, right? We recall it from the little, the summary sheet that we had at the beginning, right? So we had that the Michael addition was the reaction between an alpha beta unsaturated, right? Basically, it's an aldol product, right? So you do an aldol to produce this alpha beta unsaturated, and this alpha beta unsaturated reacts with an aldehyde and or ketone. Sorry, or ketone, not and or. It has to be but this particular aldehyde or ketone is special, right? So it has to be a carbonyl. It doesn't have to be exactly a ketone or an aldehyde. It can be an ester. It can be, even an amide. But it has to be activated. Now, what is that activation? That's what we're gonna go over in a second, okay? But we need an activator, a special type of carbonyl compound, and the product is a 1,5. So, but if we go back to the slides, right, you guys will notice that here is the aldol precursor. The aldol precursor is really an aldol. It's an aldol condensation. So basically, to do a Michael, you first need to do an aldol, right? And then when you guys get the alpha beta unsaturated, remember the alpha beta unsaturated is stabilized by resonance. Okay, so let's do the alpha beta unsaturated. Let's say that I'm doing an alpha beta unsaturated, and then I got this compound. By nature, this compound is stabilized by resonance, meaning that here I have one resonance. And then this one moves this way. Okay, so if you look at the resonance structure, so where are the double, right? The delta plus is located. You look at this compound here, the delta plus is right here and also here. So this side, this particular carbon in an alpha beta unsaturated is activated, meaning that it can receive electrons. Anybody that has electrons can donate to this particular carbon, which is the end, right, of the alpha beta unsaturated. Okay? So that's why we need to remember that the alpha beta unsaturated, what we will call the Michael acceptor, right? The Michael acceptor will accept electrons from that side, from the end of the alpha beta unsaturated, okay? So the head could be the oxygen, which is negatively charged, but remember, the oxygen is not gonna react, it's a carbon chemistry, so we will react with that. So if that's the Michael acceptor, who is going to be the Michael donor? The Michael donor are series of compounds that they have to be special, as we mentioned it before. Okay, so this one is like a map, right, of the electrophilic centers, for electrophilic and nucleophilic centers of the alpha beta unsaturated. So you have 2 electrophilic centers. So right here, let me get the pointer. Okay, so here you have the 2 electrophilic centers. So here's where the Michael will occur. The Michael will not occur here. The Michael will occur at this point. Okay, so the delta minus is no use. So this one is the activated carbonyl compound. Okay, so this one is the summary of a Michael. So that's what happens in a Michael reaction. But first, I want to start with this type of the carbonyl compound. These are the specific Michael donors and Michael acceptors. You can see that the Michael donor, right, it has to be a diketone, a diester, a ketoester, acetonitrile, nitro, right? So in my case, I'm not going to be using nitros. I'm not going to be using copper. I might be using diketones, also dialdehydes. I mean, they forgot, they skipped the dialdehyde, but dialdehyde should also be reactive. Dialdehyde, diketones, diesters, ketoesters, right? Dialdehyde, aldehyde ester, aldehyde ketone, yeah, they work. And the ketonitrile, okay? As long as they are like spaced out, meaning like 1, 3, right? Spacing, right? So, and the microacceptors, they are all the alpha beta unsaturated. They can be an alpha beta unsaturated aldehyde, alpha beta unsaturated ketone, alpha beta unsaturated ester, alpha beta unsaturated amide, alpha beta unsaturated nitrile. Okay, so alpha beta, even alpha beta unsaturated nitro. Like, so all those groups, they can work as a Michael acceptor. I will normally focus on the ketones, aldehydes, and esters, but that doesn't mean that in the quiz on the exam, you guys can receive an amide. Should not be surprised if you guys receive those. But the one that I'm telling you right now, that is that I will never, ever will use the nitro as a donor and a cuprate, in this case, a cuprate as a donor. So anything else, yeah, can be used. Even this one, this nitrile I want. No, don't worry. So, but the nitrile, yeah. In other words, the nitrile and the amide might be some surprises in the next semesters. All right. All right. So that's the whole point. So the Michael donor and the Michael acceptor. So basically, here's where this nucleophilic center will attack this particular site. Okay. The mechanism. Oh, here's a Michael donor, and this is not a Michael donor, because you might be saying, like, but professor, they're both carbon alpha hydrogens that are deprotonated. Why are they not the same? Because you need that hydrogen to be very acidic and also very stable. It's very stable as an intermediate because that one is stabilized double, right? It's double stabilized by resonance. Stabilized this way and stabilized this way. This one is only stabilized halfway. So that hydrogen is not expected to be that stable. Oh, sorry, yeah, no, it's not that stable because it's only stabilized by one C double O. Okay, so here, this, if you are using a regular ketone as a Michael donor, is not going to be obtained in good yields. Right? So it's really, really poor. You need an activated Michael. So this is the activated, Michael donors. So a diketone, diester, ketoester, ketonitrile, dialdehyde, aldehyde ketone, aldehyde ester, aldehyde nitrile. Okay. Okay. So mechanism, right? Let's do the mechanism for this reaction. Well, actually, this is the Robinson annulation. Yeah, this is the Robinson annulation. I forgot to put the things. I will do it in a minute, but yeah, let's go over the mechanism. I know that you guys like to see the mechanism for the reaction. Okay, so we will have the diketone. Okay, this one will be reacting with an OH. Remember, if you have a diester, remember that the base has to be the base of the ester, right? In this case, you have an alpha hydrogen. Let me do the blue. I will use the anion enolate. And the anion enolate, which is your Michael donor, right? Because remember that stabilized, double stabilized by resonance, will react with the alpha beta unsaturated. In this case, alpha beta unsaturated ketone. Okay, so that alpha beta unsaturated ketone will be accepting the electrons from that, right? And you will place it in that side. Okay, and then with water or acid, right? Let me double check just in case. It's an acid, okay? In acid, as a second step, it protonates that particular, right? C minus. And this is how you got, oh, here it will be, right, wedge and dash. In this case, you will get two, right? You will get two, the chiral center in this case. Okay, so how do we recognize a Michael? Michael is a 1,5 dicarbonyl, right? If we recall from our scheme, right, it's a 1,5 dicarbonyl. 1,5 dicarbonyl compounds is 1,5. So it's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That's how you recognize a Michael product. Okay, so that's by doing the mechanism as before. So we don't want to do that, right? We want to create a Michael without going through the entire mechanism. Okay, so let's say that I have this diketone, and then they tell me, okay, this diketone is gonna be working with I mean, what yeah, maybe why not this one? That's an aldol. Yeah, I know it's a cyclic aldol. It's not the conventional aldol that we saw before, but it's an aldol. It's actually a Robinson condensation, but let's just at this point let's just think that it's an aldol. So can I put can I make the connection? Yes, of course. So you guys will have the the activated Michael donor, which is the diketone or dicarbonyl compound, 1,3-dicarbonyl compound, and then you guys will make it face the carbon number 4, right? Or the end of the conjugation of your aldol. In this case, I will make it face that part. So this one is the last carbon of the conjugation of the alpha beta unsaturated. So all I will do is erase this double bond and place this single bond. That's how you're gonna make it. Okay, and then you can see double check that is 1, 5, 1, 2, 3, 4, 5. Perfect. This is a Michael addition. Now you might be saying like, Professor, but why is it important? I mean, that doesn't really make sense. At least the aldol made sense because the aldol is an alpha beta unsaturated. I see the stabilization, the resonance that we gain. The Claisen, I see it because you are basically condensing, right, two esters, two functional groups. But here, to me, it doesn't really make sense to condense, you know, a diketone with an alpha beta unsaturated. I mean, what is this type of compound? I mean, technically, we can use anything that we create, but is there any application? Yes, because the Michael, remember that the Michael is the precursor for the Robinson. So really, the Michael is like a intermediate, right? So it's an intermediate to do the Robinson. You cannot do Robinson without Michael. So that's why we have to learn Michael after the aldol. Aldol is important by itself, but Michael will lead you to Michael. Sorry, aldol, yeah, aldol will lead you to Michael, and Michael will lead you to Robinson. Robinson is the one that has a lot of applications, okay? So that's the most important one and condenses everything. Okay, great. So that's one. Let me see another one, another case. Let's say a keto ester, a Claisen. Yeah, this is actually a Claisen product, this one. And then we make it react with, yeah, with this compound. So they tell me, draw the Michael. Okay, I'll draw the Michael. So you guys will put the Michael donor. You know which one is the Michael donor because it's the one that has the two, right? The two electronegative or polar, right? Delta minus, in this case, two carbonyl compounds. And then I will draw the Michael acceptor, which is the alpha beta unsaturated. So if I want to do it, yeah, that's that compound, right? You see, I'm facing the carbon number 4 from the acceptor with the C double. So I will erase the C double bond, right? The C double C. It will be a single bond, and now we'll connect it. That's it. That's all you guys need to do. 1, 2, 3, 4, 5. Yeah, that's my Michael product. Now, how do you go back, right? Because that's also the whole point. So now, now that you guys know how to put together molecules, now you also want to break it. Well, you guys want to break it, yeah, no big deal. Yeah, that's a Michael, 1, 5. So when you guys want to break a Michael, right? So you guys have to start the numbering. 1, 2, 3, 4, 5. Now you will say, how do you know it's 1, 5? It's not 1, 5. It's not right to left. Because you always start numbering from the COO group that is closer to the donor, right? It's the donor. You can see that this one is the Michael donor because it has the two carbonyl compounds. Okay? So the one that is closer to the other COO, right? So you guys will have two COOs, but one of the two will be closer to the second COO. or maybe to the nitrile, or maybe to the ester, or maybe to the amide, whatever it is. But it's going to be closer to somebody that is also electronegative. So in this case, this is the group. So that's when you start numbering here. Okay. Next, you guys are going to cleave between 2 and 3. Again, remember the same thing as in Claisen, right? We cleave between 2 and 3. So here you're also going to cleave between 2 and 3. 2 and 3 will cleave, cover it. The number 2 gets nothing. And the number 3 gets a double bond. Double bond. And that's your Claisen. That's your Michael. But now it doesn't stop there. Why? Because this one is an alpha-beta unsaturated. Most of the question will not tell you just do the reverse Michael. They will tell you go all the way to the smallest molecules. So remember that this is an alpha-beta unsaturated. If it's an alpha-beta unsaturated, that means that you can do a retroaldol. So you have to do the retroaldol. So, okay, let's see. Okay, those are your two compounds. Can I do retro something here? Okay, retroaldol. No, because retroaldol has to be an alpha-beta unsaturated. This is not alpha-beta unsaturated. Retroclaisen. No, because Claisen is a beta-keto ester. I don't see a beta-keto ester. Is this a Michael? No, because it's not 1,5. It's a 1,3, 1,2,3, 1,2,3. Oh, well, you could say like 1,5. No, because it's not with a Michael donor, right? This one is an aldol. So aldols, we recall from earlier in this lecture, you cleave right the double bond. The one that has the double O gets nothing. And the other side, which is this carbon, right, gets a double O. And that's it. Okay. Anytime that they tell you go retro something, we have to go fully retro. So it's not only retro Michael or retro, no. We are supposed to apply the entire knowledge that we have. If we can do a retro Michael, well, do a retro Michael. But if the Michael give you an aldol product, of course you have to do the retro aldol. Yeah, you have to go all the way. Don't assume that, oh, I only do retro once. No, do retro all the way, because the most important purpose in organic chemistry is to really go to the tiniest particles, the tiniest molecules. So you start building larger molecules, like a very, very complex compounds. Okay, another one. Let me see another one. Okay, in this case, they show me this compound. I can definitely tell that this one is a Michael. Why? Because it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So both ways is 1, 5. So I know it's a Michael. So let's go retro Michael. So according to what we just discussed, so we have to cleave between carbon 2 and 3. So I have start counting. So 1, 2, 3, 4, 5. Okay. Why this way? Because this carbonyl is closer to the other carbonyl. This is not, right? This is, you can see, it's plain. It has nobody nearby. This one it is. It doesn't matter. Professor, what if I can start counting 1, 2, 3? That's okay. Because remember, this is part of the same Michael donor. The two are 1, 3. So it doesn't matter if I do 1 through 5 or 1 through 5. It doesn't matter. It won't affect it. Okay? Cleave between 2 and 3. Okay, between 2 and 3, hide the number 3. And to that, whatever is left, you guys are not going to touch it. So you just will have the same compound. Okay? And to the 3 and below, you guys will do a double bond on carbon 3, meaning that now it's going to be this. Okay? That's what you have. Okay? So this one was used to be 1, 2, 3, 4, 5. Yeah. And you want to match the numbering, right? 1, 2, 1, 2, 3, 4, 5, 3, 4, 5. Okay, now look at the compounds. Can I do retro something here? Actually, yes, here definitely, right? Because it's an alpha-beta unsaturated. If I will do an alpha-beta unsaturated, means that it's a retroaldol. Okay, In a retroaldol, you guys cleave the double bond. The double bond, the side that has the double O remains intact. Okay, and the other side, which is that carbon, gets a C double O. Good. That's that. Now the other one, can I do retro something on the other one? Actually, yes. Why? Because this one is a beta keto ester. Beta keto ester. I can definitely do a retro Claisen. So here was retro Aldol. And now I'm gonna do a retro Claisen. Okay. So what should I do in retro Claisen? The 1, 3, right? 1, 3, and then cut between carbons 2 and 3. If you don't remember how we do the sampling, please go back to the recording and then go to the Claisen part. The Claisen is how we go the retro. Cleave between 2 and 3, cleave here. The ester, the carbon number 2 will get nothing. And the carbon number 3 gets the ester. Okay, you see 1, 2, 1, 2. And this one is 1, 2, 1, 2. Right? Yeah, that's my tiny pieces. So that whole molecule that you saw here, this one that you see right here, was made by simply this butanone, formaldehyde, ethyl acetates. Yeah, 2 ethyl acetates. Yeah. See, that's the whole point of organic chemistry, is that by using tiny things, you know, you use them as building blocks to construct bigger molecules or more complicated molecules. That's what we call total synthesis. So total synthesis, what you guys do is you have a molecule, it's a large molecule. Normally in pharmaceutical industry, you know, medicinal plants, what they do is they extract these active compounds. For example, you know, antibiotics or antimicrobials, antivirals. You know, they collect these plants that they are known to have, you know, these properties. They isolate the compound that they believe that is responsible for that particular property, and they start identify, right? They use NMR and IR to see the structure. Once they elucidate the structure, is that they start breaking it apart. So maybe, okay, so I have this molecule. Let's try a retrowitic. Let's try a retroimine. Let's try a retroenamine. Let's try a retrogrignard. Let's try a retromichael. Let's try a retroaldol, whatever, right? So remember, in organic chemistry, there are like, if not thousands of reactions. So some of those reactions should match the particular compound that you are making. Okay, so that's the whole idea. Use this as an example. Remember that these are examples. I do a lot of examples during the lecture, so use this as a particular way how to practice as well. Okay, so let's see another Michael reaction, another retro Michael. Let me see. Yeah, let's do a. Okay. Yeah, that is. They tell me this compound, right? So let's break it apart. They tell me break apart this compound. Okay, so first of all, I have to recognize that I can do a retroaldol, retroclaisen, or retromichael, right? The alpha-beta unsaturated is a retroaldol. So for example, this one is an aldol. I can see clearly it's an alpha-beta unsaturated. Do I see any alpha-beta unsaturated here? No. Do I see any Claisen? No, because there is no ester. To do a Claisen, I need to see an ester. I don't have a Claisen. Aldol, yes. So we'll start doing with the aldol. Break the aldol. So the aldol, breaking the double bond, the C double O side gets nothing. Okay, so one of the pieces that I will have is this compound, right? And the rest is what? The rest is going to be all this fragment. And of course, the other side, guess what? The other side gets the C double O. Okay, now let's find for another aldol. Is there any other aldol? No, because I don't see any alpha beta unsaturated. Okay, so there is no aldol. Is there any Claisen? No, I don't see any ester. Michael. Okay, let's look for Michael. 1, 5. 1, 2, 3, 4, 5. Good. Is this also Michael? 1, 2, 3, 4. No. 1, 4 is not a Michael. So don't try to do a retro Michael here. Right? So it has to be a 1, 5. And not only is 1, 5 is not enough. The 1, 5 has to be, one of the sides should be a dicarbonyl. Right? So this one is a perfect Michael. 1, 2, 3, 4, 5. What is the rule about Michael? Cleave between 2 and 3. What happens with the number 2? The number 2 gets nothing. So break it. And what about the rest? Well, the rest you have to do a double bond on number 3. Okay, this is number 3, 4, 5. This one will split. This one, and then that's the double O. Okay, good. Okay, I broke it apart, right? The Michaels. Now, can I do anything here? Yes, I see an aldol. Okay, break that aldol. Break it here. This is an acetone. And the other side is nothing. Like it's nothing. I can't do anything here. So don't try to force it. You don't always have to be retro something, right? So in this case, it's 1, 4. There is no 1, 4. We haven't learned any 1, 4. So just leave it alone. Okay, that's it. So the starting material for this compound, I will put it here in blue. 1, 2, 3, and 4. So this complex molecule was made from this one, right? From this one, with this one and this one, and they're all commercially available. No, I'm not sure about this one, but you can buy acetone, you can buy cyclohexadione, you can buy this one. This is 3-methyl butanol. Yeah, that one is commercially available, definitely. Right? So from those molecules, you can easily make this compound. Okay, maybe this compound is antimicrobial, maybe it's anti-pests, right? To fight ants, to fight, let's say, mice, or to fight, I don't know, any compound can have this particular shape. Okay, so that's the whole point, to do retro something. Okay, so now to finish that, we will do the well, that's all about Michael. Now let's do the end. So we're close to the end. Are you guys happy, excited? Hey, so the last one is the Robinson annulation. I know it says Michael addition, but it should be really Robinson annulation. The Robinson annulation here, this part is the Michael addition. This is the Michael because you have a 1, 5, 1, 2, 3, 4, 5. But then if you to the Michael product, if you apply heat, well, base and heat, right? So sodium hydroxide and heat, you guys will do an aldol condensation on a Michael. An aldol on a Michael is called Robinson. Robinson annulation is the next and last reaction we will study in this chemistry 240. So Robinson annulation, as the name says, the Robinson annulation, the purpose is to make a ring. And you can easily see the ring right here. And it has to be a 6-member ring. Okay, so it is a 6-member ring, similar to what's the name? Diels-Alder reaction. Okay, but it is an aldol inscribed in one cyclic compound. Can it be a 5-member ring? No, actually it has to be a 6-member ring. Yeah, it has to be a 6-member ring because it's a 1, 5. It's a 1, 5. So the spacing is 5 carbons plus the terminal alpha carbon that makes it 6. So it has to be 6-member ring. Okay, so how does that work? Well, the mechanism is a little bit complicated. I mean, complicated in the sense of how crowded it gets, but we can do it. Definitely, absolutely, we can do it. This one, okay? So they tell me OH minus. So the OH minus, I will deprotonate right here. This one. You will tell me, Professor, but from what I see, right? So this one should be the most acidic hydrogen. Why are you removing this hydrogen and not this one? This one is the most acidic. True, this is the most acidic. But remember that to do an aldol condensation, you need to lose two hydrogens. Two hydrogens must be lost. Okay, this alpha carbon does not have two hydrogens. So you can do an aldol here. So you need to lose two because remember you are making a double bond. Double bond means that you need two bonds. So this one only has one hydrogen. It can't do it. Okay, so that's why the next one will be this one. Say like, Professor, why don't you use this one, which is more internal? Yes, but if you do an aldol here, you will get a very short, a very small ring. Remember, 4-member rings are not as stable. 3-member rings are not stable. 5-member rings are stable. 6-member rings are stable, but 6-member rings are even they have the boost of the stability because of the the chair conformation. So well in the it gets that extra energy from the that's why it has to be this particular card. Okay, and then take my word because yeah, it has been proven. So whenever you guys do a reaction like that, Robinson, it has been, identified, right, 6-member ring as the final product. So it does work this way. Okay, so the oxygen attacks, gets the carbon ion enolate, minus. And remember, it's an aldol. So you're gonna do an aldol here. So the aldol, this one will be the aldol donor, will attack the aldol acceptor. It can be this or this, it doesn't matter because in this case the molecule is symmetrical. So basically we'll do an aldol. I'm just repeating the aldol because I mean it is okay. You guys want to keep track. This carbon, right? Of course, it's gonna be this carbon. This carbon has a methyl side chain, and next is the C double O. Okay, and this one will be right C double O. This one, and attached to the ring. Okay, good. So what is next? Well, technically, it's the protonation. Right? Because that's the aldol. It's an aldol, really. Then comes another OH. Right? Once again, it's an aldol. Deprotonates. Where is it going to deprotonate? This alpha hydrogen. That one. And then here's where you lose that, right? The leaving group, right? The OH is a leaving group. Comes down here, and then the OH is lost. That's the mystery, right? Of the aldol condensation. Ta-da. Yes. That's it. That's the Robinson annulation. It's an aldol that creates a 6-member ring alpha beta unsaturated carbonyl compound. Okay. Interesting, right? So very, very straightforward, very beautiful reaction. How you can make a 6-member ring with this reaction of alpha position. Okay, let me see if I find some additional examples for you guys to do either retro Claisen or retro. Right here I had some few. Yeah, the mechanism. Yeah. Okay, so let's do some retro analysis. Okay, so let's say that they tell me go retro on this compound. Okay, so if they tell me go retro this compound, yeah, I have two examples for this. Yeah. Okay, retro here. So first we have retro Robinson, retro Michael, Retroclaisen, and retroaldol. So here I see a retroaldol, right? I see the aldol. Now here, is this a Claisen? Is this a Michael? 1, 2, 3, 4, 5. Could be, could be. But I have a double bond inside. So you always start with the aldol. That's the most logic idea. Okay. So I have an aldol inside of a six-member ring. So that means that it's a retro Robinson. But the retro Robinson, there is nothing different. You just always cleave right in the middle. So you guys will have this compound. Dun, dun, this. Okay. Down, down, down. OET. Right. And this one gets the C double O, right? So you do a retroaldol here, the cleavage, the one that has the C double O side gets nothing, and the one that has no C double O gets C double O. Good, done. I did Retro Robinson. Retro Robinson will always take me to the Retro Michael. So Retro Michael, let me see. 1, 2, 3, 4, 5. Good. 1, 2, 3, 4, 5. Perfect. So I will start doing the 1, 5. So does it matter where it, well, these two are closer. So this one should be the number 1. Okay, let's do retro. Retro Michael tells me cleave between 2 and 3. Good. Cleave between 2 and 3. So the 2 and 3, I will get two compounds. First is that you guys will have, right? Number 2 gets nothing. And number 3 gets a double bond. Okay. Two compounds. Now, can I do something to this one? Yes, this is an alpha beta unsaturated. Perfect, beautiful. Okay, it's an alpha beta unsaturated. Then I cleave right at the double bond. If I cleave at the double bond, I will have two pieces, right? This side with the double O gets nothing, acetone. And the other side has a C, it's just a C double, meaning that it gets a double O. Good. Those are my two starting materials from this side. Now here, what is this, guys? We just did it, right? A few minutes ago. This is a Claisen. Why? Because it's a beta keto ester. So Claisen tells me 1, 2, 3, start numbering from the ester side and cleave between 2 and 3. To the 3 side, put an ester. And to the 2 side, do nothing. And you get your starting materials. So 2 ethyl acetates, 1 acetone, and 1 formaldehyde. See, those tiny bits are enough to make this particular compound, which it looks very complex, right? So that's what is needed, right, to make that particular synthesis. All right, one more. Okay, maybe the last one for the Michael. I know that you guys are excited. You want to just go right now and go and study all these reactions. All right, so the last one is also one that involves retro Robinson. Yeah. Okay. Let's break it. First, I identify the Robinson. How do you know the Robinson? It's a 6-member ring with a conjugated alpha beta unsaturated. So cleave it, right? Cleave that the double bond. If you cleave the double bond, I'm going to turn the molecule a little bit this way so you guys can see it better. I will put it like this. So you guys, I want you guys to see it better, the molecule. This is really what it is, this compound. Okay, so that double bond gets broken, right? The side that is closer to the double O gets nothing. The other side gets the double O. Yeah. I see retro Aldol. Well, not really Aldol. Retro Robinson. Now here, I have to do a retro Michael. Michael is 1, 5. So I can see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, good. I start numbering from those two neighbors, right? What is next? Cleave between 2 and 3. Good. To the number 2, do nothing. And to the number 3, get a double bond. Now, do the analysis here. What is this? Well, this is an alpha-beta unsaturated, so definitely it's going to be a retroaldol. If you break the aldol, break it, so you get this one to the double O side, do nothing. That's acetone. And the other side is a simple C double, meaning now becomes C double O, formaldehyde. Okay. And the other side, of course, is a Claisen. It's a beta keto ester. So do the Claisen. 1, 2, 3. Break it between 2 and 3. To the number 2, do nothing. Methyl ester. And to the number 3, complete it with an ester. So 1, 2, 3 ester. Okay. Ethyl acetate, methyl propanoate here. So that will be my 4 starting materials for this particular Robinson, right? All the way from Robinson, Retro Michael, Retro Aldol, Retro Claisen. Here's a Retro Claisen. Right? So that's really the end, okay? So, I mean, please just go to the notes. There are many old exams, old quizzes. That's the way really how to address all these reactions. If you go to the slides, this particular slide, there is no synthesis. I will not use synthesis in this particular chapter. It's all about how to make molecules, but there is no synthesis. Do retroanalysis because this alpha chemistry is all about retrosynthesis. So you guys will most likely get a large molecule and then we'll have to break it down. Okay, so but like synthesis, like properly said, no. Right, but maybe the malonic ester and maybe the acetoacetic ester, that's it. But it's reduced to that. But synthesizing, doing synthesis using Michael Robinson, no, that would be too much. But doing a retro Michael, Retro Robinson, Retro Aldol, Retro Claisen, that's definitely most useful because that's the one that how you guys will address the retrosynthetic analysis. Okay, so that's really it about our chapter, and then that's really the end of my mission being here, your instructor for Organic Chemistry 2. I know that some of you have taken me as an Organic Chemistry 1, and now you're taking me for a second semester. Thank you very much for your preference. Really, the purpose of organic chemistry, you might say, like, Professor, am I going to be seeing, Claisen, Robinson, Grignard, D.L. Solder in the next classes, biochemistry, microbiology? No. To be honest, you are not going to see those reactions. But really, something that teaches organic chemistry that does not teach any other or chemistry class is the critical thinking. Is how to assemble, how to put things together, how molecules connect, right? So something plus can only target something minus. An empty orbital only targets a full orbital, right? So something that has electrostatic hindrance is only going to target something that is hindrance free. That particular thinking applies to biological systems. Cells are smart, and then cells are nothing else than larger organic molecules. So even though you guys are not going to be doing these reactions, name reactions, but the same rationale, the same idea of valence, right? Or covalent bonds, ionic, hydrogen bonding, right? So all this, or how things got together, that's really the purpose of organic chemistry. Okay, so to improve your strategies, like problem solving, situations that you guys will find yourself, like, how can I break this molecule? Well, you have to break it, using certain rules. Because you cannot just break a Robinson because you want to break it anywhere. No, there are some rules to break Robinson. There are some rules to break a Michael. Same thing, you guys will use it in biochemistry, in microbiology. There are some ways how you can break glucose in metabolism, in glycolysis. There is some rules. I want to break, let's say, coconut oil. When it goes to my cell, how does it get broken? Can I break it anywhere? No. There are some specific sites of coconut oil that can get broken. Adipic acid, lactic acid. Why somebody is lactose intolerant? Because there is an enzyme. What happened with that enzyme? Why that enzyme is so special? Or because maybe that enzyme has a steady hindrance. That's not really, let's say, like an alcohol or a glucose that is, it has a particular branching, is special. So you see, you're applying all those. Okay, so that's why I just wanted to, that's the take-home message after these 2 semesters of organic chemistry. Congratulations, you made it this far to chapter 21. There are many more, I mean, chapters that are coming after. We haven't done really carbohydrates, amines, organometallic, lipids, amino acids. Those you guys will see it in a future course, biochemistry. Everything, comes down to carbon, nitrogen, oxygen, and hydrogen. Okay, so that's the whole point. Hopefully you guys enjoyed. I mean, I did my best, and definitely there is a lot of room for improvements. Please let me know your comments. If there is any questions, please feel free to come to my office hours to see me, during the lab, after the lab, before the lab. Uh, you know, there's always plenty of opportunities for us to not only to talk about organic chemistry, but I will be also very happy to talk about your careers. Let me know what are you planning to take next? Ask me for recommendations. What is chemistry? What is biology? Why not biology? I mean, I know sometimes I make jokes about biology, but biology is also a very, very, very rewarding career, and anything in STEM. I mean, definitely physics, mathematics. I mean, math, you have to take it because without math you cannot do chemistry, unfortunately. Physics is a lot of applications, so if anybody's there in any STEM career, please let me know, or even simply ask me, like, what does a chemist do besides teaching chemistry and organic chemistry and memorizing 50 plus reactions? Or what does a biologist can do in the later on? So what is graduate school? What is what's the master's program? What is the PhD program? How can I secure a spot in a PhD? When do you need a PhD and not a master's, right? So all those questions, please feel free to ask me. Right now, you guys at that point, organic chemistry is a 200 level course. So you are definitely one step from finishing. So organic chemistry is not just like an extra class. So you guys have to definitely keep going and then surprise me, I mean, with a chemistry major or a chemistry minor, or taking some other classes in chemistry. So definitely that's in personally, I mean, I'm a chemist. Of course, I want everybody to be a chemist, right? To be talking the same language, but I'll be happy, I mean, for you guys just to finish your degree in STEM or anything and then continue with your program. That's the whole point. Okay, so nice meeting you all. I'll be in contact with you. I know that I will be see each other. The STEM community is very small, mostly in the East Coast area. Even if you go to other states, we'll be always in contact. Okay, so I'll be happy to hear about your success. Congratulations once again to me for making it all the way to chapter 21 organic chemistry 2. So I'll be in contact with you soon. Take care, and then nice meeting you. Then let me know if you guys have additional questions. Bye bye.